Hey grade 12s, so if chemistry is getting a bit confusing, we're about to break down question 1 of the June 2025 chemistry paper. So we're about to look at the various questions that they ask in question 1 that span topics such as organic chemistry, rate of reaction, chemical equilibrium, and acids and bases. So let's jump right in. So question 1.1 says, which of the following represents a saturated hydrocarbon? So this is an organic chemistry question, and we have a couple options. We have A, C2H4, B, C3H6, C, C3H8, and D, C4H8. So each question is a 2-mark question, and what we have to first understand and distinguish is the difference between saturated and unsaturated. So a saturated hydrocarbon is a hydrocarbon chain that has single bonds only, and then an unsaturated has double bonds and triple bonds in the mix in the hydrocarbon chain. Cool. A nice way that I like to remember that saturated is single is that I sat down to sing, is a little memory device I use to group sat and sing over there, and then that just means that the unsaturated is the double and the triple bonds. And then what we have to know here is, because they are giving us different hydrocarbon chains with different amounts of carbons and hydrogens, is the standard formula for a saturated single bond, where we have CnH2n plus 2, and this tells us how many C's there are and then how many H's there are relative to the C in a single saturated hydrocarbon chain. A double bond over here, a reminder, is CnH2n, and then a triple bond is CnH2n minus 2. So single is H2n plus 2, a double is just 2n, and then a triple is 2n minus 2. So there's a little pattern there of plus 2, plus nothing, and then minus 2. That means we just have to look for an option that fits this formula over here. So we have to see 2 and 4, that does not work because that does not fit this formula. That fits this formula over here. If we have 2 ends and then 2 times 2 is 4, that means A is a unsaturated double bond. And then again, C3H6, that is the same relationship where it is just multiplied by 2, so that means that is also a double bond, an unsaturated hydrocarbon. And then C over here says C3H8, so we got 3 there, and then 3 times 2 plus 2. Does that fit this formula? Because we had 3 over here. 3 times 2 plus 2 equals 6, 8. So we got 3 and 8, and that does work for us. So C is our answer over here, and then we can just quickly check that C4H8 for D is exactly the same as A and B, fitting a double bond, an unsaturated hydrocarbon. So that means our final answer here is C for 2 marks. Cool. And then 1.2 here says, which of the following pairs of reactants can be used to prepare the ester called ethyl propanoate in the laboratory? So we have 2 options. An esterification reaction has to do with an alcohol and an acid, a carboxylic acid specifically. So that means we have to look at an alcohol and an acid. Alcohols end in ol, and acids end in oic. All of these options here end in oic. So we're about to break it down. So this is what we're looking for. So off the bat, we can rule out anything that doesn't end in an ol or end in an oic acid. So that means A over here is ethane and propanoic acid. We're also looking for the correct prefixes where we have our meth, eth, prop, but, pent, for example. So we need the corresponding eth and the corresponding prop for these guys. Ethane is a hydrocarbon. It is just a single bond, and that is not an alcohol, so we can eliminate A over there. Okay, B is propanol and ethanoic acid. Okay, we have an alcohol, we have an oic acid. We can keep that option for now. We can see if there are any other alcohols. And then C over here says ethanol and propanoic acid. Okay, that also has an alcohol there, except the eth and the prop and the prop between B and C are swapped. Okay, so we just need to see if it is one of those options, which one is corresponding and correct with the initial ethyl propanoate that we are comparing to. And then D over here says ethene and propanol. This is an alcohol and a double bond of a hydrocarbon, which means it doesn't have an oic acid. It does not have an acid for the ester reaction, which means D is out. So what this means is that we have 2 options here. We have an ol and we have an oic. One thing to keep in mind is that ethyl propanoate, the "-ile" comes from the alcohol. In order to create an ethyl, we would need an ethanol, because ethanol is the alcohol we're dealing with, and our suffix, our "-ol", always turns into an "-ile" in esterification, which means we have ethyl over here, and then propanoate comes from the oic acid, so the oic acid turns into OH. over there, which means we have our propanoic acid, and that turns into propanoate over there, which means we end up with ethyl propanoate. And that means we had an ethanol and a propanoic acid, and that formed our ethyl propanoate up there, which means our ol turns to il and our oic turns to OH. And working backwards, it means our OH has to turn to our oic acid and our il has to turn to our ol over there, which means our answer is C, because we have an ethanol and a propanoic acid and they map accordingly, compared to B, where we have the propanol, which is the alcohol, but the alcohol doesn't turn into the OH over here. The alcohol turns into the il. So this propanol would turn into propyl, and that isn't what we have in the split for this esterification reaction, which means B is out and C is our final answer there for 2 marks. So 1.3, consider the reaction represented by the equation below. We have CH3CHCH2 plus HBr goes to CH3CHBrCH3. So I'm going to draw it for us just now because it helps to draw any organic chemistry reactions, especially when they are structured like this. So we can visualize and see what is moving, because it is a lot easier to see that with the structural formula than this formatting over here. But they are asking us what type of reaction is represented above. We have A, halogenation, B, substitution, C, hydrogenation, and D, hydrohalogenation. So this is 2 marks over here. So I'm going to draw it quick and then we can rule out which ones it isn't, so we can find which one it is. So I've just drawn it here. We have this initial guy over here and it has a double bond, because if we drew the amount of C's and the amount of hydrogens we needed on each of them, we would see that we need a double bond because carbons can hold 4 hydrogens always, which means we were a couple hydrogens short, so we needed to form a double bond based on the amount of hydrogens that they had here. And then we added an HBr as they had over here, and then I just drew the line down here for the product that we formed, where our double bond ends up breaking and this HBr gets added to both. So we now can visualize it a bit easier. So what we're dealing with is something going from 2 reactants to 1 product. So it is some type of addition reaction, because a double bond is breaking and we are adding this. Elimination is just working backwards, going from one thing, eliminating it, separating it, and forming a double bond or a triple bond, for example. So the reason I'm mentioning that is because B over here is substitution. So if this is an addition and elimination is working backwards, substitution is just swapping something, meaning we don't go from a double bond to a single bond or a single bond to a double bond. We just go from a single bond to a single bond or a double bond to a double bond, because we are just swapping something. So a substitution is therefore out here, and that does not work because we are not just swapping something. We are breaking a double bond and forming a product with only single bonds. So that means we have a couple options to look at, which are more specific and aren't just the grouped headings of addition, substitution, or elimination. So that means A, halogenation. A halogen is anything in group 7, like our bromine, our chlorine, our iodine, and that is what we usually add when we are doing a halogenation. In this case, we didn't just add the bromine. This hydrogen didn't go off elsewhere and join another hydrogen to form H2 or something like that, which means it isn't just halogenation because we didn't just add a single bromine to this. Therefore, we can rule out A, our halogenation over here. Then our C over here, hydrogenation, is when we add just a hydrogen over there, which isn't what we have here. We don't have an H2, we have an HBr, which means we aren't dealing with hydrogenation. So therefore that guy is out, and that leaves our final answer as D. And we can see why it is true is because it is hydrohalogenation. That means we're adding a hydrogen over there, and the halogenation means we're adding a halogen over there, and we are in fact adding the H and the Br, and they are both attached on our product on the right side. So that means our answer is D, hydrohalogenation, for 2 marks. So at this stage, we're on 1.4. 1.4 says, consider the following compound. Okay, so we have CH3CH with a little bracket Cl. A reminder that these little brackets imply side chains. Then we have CH2C and then another side chain, CH3, 3. So that means there are 3 of them going that way. Let's check out the question, and then I'm going to draw this for us. So the IUPAC name of this compound is A, 2-chloro-4,4-dimethylpentane, B, 2,2-dimethyl-4-chloropentane, C, 4,4-dimethyl-2-chloropentane, or D, 4-chloro-2,2-dimethyl pentane. So I'm going to go ahead and draw it for us along, and then we can see which one corresponds with it. So we have something like this over here, where we have our CH3, C, 1, 2, 3 H's, then we have a CH, we have our C with an H over there, and then our Cl on the side chain over here, then we have a CH2, we have a C with an H and an H over there, and then we had our C coming out here, that is this guy over here, this C over there, and then we had 3 CH3s, and this part was a bit weird when I was drawing it, but if they all have 3 H's, it means that they all are branched off like this, because this is the only way. They aren't stacked on each other, because then they will end up with 2 H's, so they're all branching off like this, where they all end up with 3 H's over there. So then we have our branch chain over there, and now we can look at the IUPAC name of this compound. So what's most important is trying to identify our long chain first. We can always look to see if our straight chain is the longest chain, or if a bend chain is a longer chain. But let's count the straight line over here. So we have 1, 2, 3, 4, 5. And if we count from here, we have 1, 2, 3, 4, 5. And if we do the same thing, it'll be 1, 2, 3, 4, 5. So it doesn't matter where we take it from, but I'm just going to treat it as if this is 1, that is 2, 3, 4, and 5. The reason I'm counting this way and not this way is because the most action is happening closest to this guy over here. By that I mean these 2 carbon chains get priority in the counting of the long chain. Even though there's a chlorine over here, it does not get priority in where we start counting our longest chain. It gets priority in where we name it, as we'll see when we find our answer, but the most action happening near the start of this long chain has to do with any other carbon side chains. And that means we have a carbon coming off here and another carbon coming off here at our 2 over there. And that means our chlorine is branching off on our 4 over here. And now we're going to look at the naming order to see which one is the correct option. So 2-chloro 4,4-dimethyl-pentane. So we have a 4-chloro, not a 2-chloro. But you see how we might end up looking at A as our correct answer if we counted our longest chain from left to right, being 1, 2, 3, 4, 5. Because then we would have a 2-chloro here, and then a 4,4-dimethyl would be happening here. But once again, we name our longest chain from the side where the most action is happening in terms of any carbon side chains, and then we'll look at any halogens or any other attachments then. Okay, which means A is out simply because it is numbered in a different order. So then we have B over here where it says 2,2-dimethyl 4-chloropentane. So 2,2-dimethyl, that is correct. So we have a 2 and a 2. Dimethyl, di meaning 2, methyl meaning 1 attachment, 1 carbon, not an ethyl. 4-chloro, great, pentane. So this looks almost correct, or at least it is numbered correctly, but it isn't in the correct order because, as we mentioned, the numbering is correct, but the order is incorrect because the way that we write it is our chlorine or any halogen first with the numbering that it has. Okay, so that means B isn't our answer, even though it is numbered correctly, but we have to write the chloro first and then the methyl later on when we write our IUPAC name. So B is out. C, 4,4-dimethyl 2-chloropentane. As we can see, numbering wise, that is also not correct because we have a 2 and a 2 without dimethyl. So C is out. And then D is our final answer. As we can see that D is very much like B, but we have written it in the correct order. We have written the 4-chloro. We've dealt with the numbering correctly, knowing that 4 corresponds with the chlorine attached to it, but we have to write that first in alphabetical order. So we're writing this alphabetically with the halogen, and then from there we're dealing with the correct numbering further of the 2,2-dimethyl branching off of this carbon over here, this carbon 2. We have the di meaning 2, we have the methyl over here, and then pentane has to do with our longest chain, meth, eth, prop, but, pent, and that has to do with our longest chain over here, and therefore D is our final answer, earning us 2 marks over there. So then 1.5 over here says 2 learners want to investigate the factors affecting the rate of reaction between magnesium and hydrochloric acid. Okay, the concentration of the acid remains the same. We are not using up the concentration of the acid as the reaction takes place. So we have our gas syringe here, we have a test tube containing magnesium over there, excess dilute hydrochloric acid. So it does not run out first, the magnesium runs out first. So which of the following changes to the experiment will produce the fastest rate of reaction? So A says powdered magnesium with hydrochloric acid at room temperature. B says powdered magnesium with hydrochloric acid at a higher temperature. C says magnesium ribbon with hydrochloric acid at a higher temperature. And D B, magnesium ribbon with hydrochloric acid at room temperature. So when it comes to rate of reaction, question 5, usually in our question paper, we usually look at 4 big things. So the first thing we look at is surface area. By that, anything that has more surface area, i.e. powder over ribbon, will react quicker because there are more particles exposed, therefore more effective collisions. Okay, compared to this guy, which takes a bit longer to break down before the effective collisions can take place. Okay, so we have surface area. We also then have temperature. So if there's more temperature, it means there's more kinetic energy to allow for more effective collisions. Okay, which means the temperature, if it is hotter, that will also increase the effective collisions. Both of these are what we're dealing with here, but I will quickly mention the other two that we will see in later questions. We then have concentration and or mass, and that will also increase the amount of substance that can react, therefore increasing the effective collisions per unit time. And then the only one that works a little bit different is a catalyst, because a catalyst doesn't increase the energy or the amount of particles for more effective collisions, but it lowers the activation energy. So a catalyst works a little bit differently from these guys, but it ultimately does help speed up the reaction without getting involved in it. So that means a greater surface area will increase our reaction, so powder over ribbon, and a higher temperature will also increase the rate of reaction. So that means we have to look at a couple things. So let's look at surface area first, where we can compare magnesium powder. Okay, so that's important. And these other two options include magnesium ribbon and magnesium ribbon. Okay, so just off the bat, fastest rate of reaction has nothing to do with the magnesium ribbon because the powder will be quicker. So now we just have to compare A versus B, where we both have powdered magnesium with hydrochloric acid, but one is at room temperature over here and the other is at a higher temperature. So if they are both powder, therefore they are both reacting quicker, but then this one is at a higher temperature, it means that B is our final answer, as powder and a higher temperature will react faster than powder and room temperature, and both of those will react faster than magnesium ribbon at a higher temperature or magnesium ribbon at room temperature. So therefore, our final answer for 1.5 is B, earning us 2 marks over there. And then 1.6 over here says, consider the energy profile graph for a reversible reaction shown below. So we have the potential energy over here, we have the course of the reaction, we have reactants, we have products, and they said that this is reversible. So it can go this way, forward, and this way backwards. One thing off the bat, something like this, what we're dealing with is an endothermic reaction, meaning that it is taking in energy and heat, which means its reverse reaction is an exothermic reaction. As it goes this way, it is releasing heat in the reverse reaction. That is just something to remember as we read the following. The following statements are given. 1. A to C over here represents the activation energy for the reverse reaction. Okay, so A to C over there represents the activation energy, but not for the reverse reaction. It represents the activation energy for the forward reaction because that is how much energy from the bottom, from the energy of the reactants all the way up to our peak, to our activated complex. Okay, but for the reverse reaction, the activation energy is just over here from B to C. So therefore, 1 is out and is not one of the answers because as we'll see, they're asking identify the correct statements over here, and we have a couple options. We have A, B, C, and D with different combinations of which statements are actually true. So 1 is out, and then 2 over here, delta H for the reverse reaction is A minus B. So delta H for the reverse reaction is A to B over here. So we have A to B. And one thing to note here in this previous interpretation, A to C means A minus C in this case. So A minus C still does not give us the activation energy for the reverse reaction. C minus A will give us the activation energy for the forward reaction, and then C minus B will give us the activation energy for the reverse reaction. And then here back to 2 again, delta H for the reverse reaction is A minus B. So A minus B over there, if it's the reverse reaction, we have our products over here and our reactants over here. And delta H is always our E prod minus E react. And if we are doing the reverse reaction, we're going from right to left, which means these are our products and these are our reactants in the reverse reaction. And therefore A minus B is correct for the delta H, the enthalpy for the reverse reaction. For the forward reaction, it would be B minus A. It would be these products minus these reactants for the forward reaction. That is just a nice way to check whether your thinking for the forward and the reverse reaction correspond. So that means 2 is correct for this one. And then 3 over here says a catalyst lowers the activation energy for both forward and reverse reactions. So a catalyst creates an alternate pathway by lowering the activation energy, making the activated complex a bit lower. So a catalyst does lower the activation energy for both the forward and the reverse reactions. It is there not taking place in the reaction, but it will offer that alternate pathway in both the forward reaction and the reverse reaction, which means 3 over here is true. So then identify the correct statements. We have to see which ones are true and which ones include only 2 and 3. And A over here says 2 and 3 only, and that is correct. B says 3 only, which is not true. C says 1, 2, and 3, which is not true because 1 is not true. And D says 1 only. So that is not true either. And therefore our answer is A, 2 and 3 only, earning us 2 marks over there. And then 1.7 over here says the reaction of an acid-base indicator, In minus, represented as HIN, aqueous, with H2O liquid, reaches equilibrium according to the following balanced equation. So we have HIN, aqueous, red, so that is the color the solution will be when it is red, or when there is more HIN present, then the solution turns red, plus H2O, our liquid over there, goes to, as we can see, it's a reaction that can go both ways, H3O plus, our hydronium, that is when an acid breaks up and we form H3Os. So our hydronium, which means our acid gave an H to our base over here to form our hydronium. And then we have our In minus, and that is yellow. When that is yellow, it means we have more of our basic solution. Considering this is an acid, this is a base, this is our conjugate acid, and this is our conjugate base. And then we have delta H over here is less than 0, which means that this is an exothermic reaction. Whenever delta H is less than 0 or negative, it means we're dealing with something like this, where we have our products and our reactants. And if we were to take the enthalpy of this, products minus reactants, say now this is 10 and this is 5, delta H is always our products minus our reactants, which means we have 5 minus 10, for example, and then we end up with a negative 5 for our delta H over there, which means delta H has to do with an exothermic reaction, means we are releasing heat, which means that heat lives on this side of the reaction. We will break this down in further lessons when we're looking at chemical equilibrium and how to interpret heat. But right now, when we are releasing heat in a reaction that can go both ways, it means that we want to write heat as if it was a compound on the side that it gets released. So exothermic means heat is released. It means as we form products, our heat is released here. If it was endothermic, we would write the heat here as it would take in the heat. This will just help us interpret one of the options here that they're about to ask. So then they're saying at equilibrium, the color of the solution is red. So it means that the reverse reaction was favored and we end up with more red in the solution, and we've also run out of H2O, we've run out of our base in the solution. So which of the following will change the color of the solution from red to yellow? So we want to favor the forward reaction. So we have a couple options. So A says increasing the concentration of H3O plus ions. B says increasing the temperature of the solution. C says adding a base. And D says adding an acid. So let's break them down and see which ones do not work so we can see which one does work. So A, increasing the concentration of H3O plus ions. So this is an acid and base question, but the setup is that of chemical equilibrium. So what happens if we increase the concentration of our H3O plus ions on this side with a reaction that can go both ways? Just like a seesaw, if we were to increase it, it would favor the reverse reaction because we have too much concentration on this side. This whole reaction is chilling inside one big beaker, but if we add more to this whole beaker, more H3O pluses, it means that our reverse reaction will be favored because we have too many H3O pluses on this side, and therefore our reaction will go from yellow to red, and that isn't what they want here. So increasing the concentration of H3O plus ions, that will cause the reaction to become more red, and that is not what we want in this case. So then B over here says increasing the temperature of the solution. So increasing the temperature, as we discussed, this is an exothermic reaction, and that means heat is on our product side over here. So just like this H3O plus ion that was also on our product side, if we increase the temperature in this whole beaker, it means we have too much heat on our product side. And therefore, just like we treated our H3O plus, too much heat means it's going to move to the other side in order to balance out this whole seesaw, this whole chemical equilibrium, which means that if we do increase the temperature of the solution, we add more heat, it favors the reverse reaction and we turn more red, which means that isn't what we want as well. We want to go from red to yellow, and if we increase the temperature, we are making this become more red. So before we look at C, we're going to look at D, because C is our answer, but D doesn't work because it says adding an acid. So my initial thinking was that if we add an acid over here, we add more of our HIN, our acid, over here, which means that if we have more of it, just like our previous seesawing, we would add more of it and that would favor our forward reaction. The reason that doesn't work in this case is because at equilibrium, the color of the solution is red, which means we have HIN, but we do not have any more base to react with it, which means that if we just add more of an acid to this guy, it won't actually favor the forward reaction going from red to yellow, because there's nothing to react with the acid in order to favor the forward reaction, because the color of the solution is already red, which means we have an acid left over, but there isn't water to react with it. And that is why an acid does not work in this case, in the same thinking that we did A and B. And therefore, our answer is C over here, adding a base. Because if we add a base in this reaction that is currently at equilibrium, while the color of the solution is red, it means that there is a base for this acid to react with, and now they can react with each other, going from red to yellow, because now we can form the conjugate acid and the conjugate base. These two guys can react, break apart, and form the H3O plus ions, the hydronium ions, and the IN minus ions. And therefore the yellow is going to form there, and that is the reason that adding a base in this specific example will turn this whole solution from red to yellow. So our final answer here is C, adding a base, and that just earned us 2 marks. Okay, so 1.8 over here says the expression for the equilibrium constant. So this is also a chemical equilibrium question. For the equilibrium constant Kc of a hypothetical reaction is given as follows. So we have Kc equals the concentration of PQ3 to the power of 2 over the concentration of Q2 over 3. So a reminder that this is our concentration coefficient, and we have our products, the concentration of the square brackets, and our products at the top over our reactants. And then any powers that they have over here, any exponents they have, are the mole numbers in front. So we're going to look at that here, like this 2 over here, that has to do with that 2 over there in the exponent. So we're about to break this down. And one other thing to remember for Kc, that even if we have used our Rice table, we do not put any solids in here. So that is something to keep in mind as we work through the potential options. So which of the following equations for a reaction at equilibrium matches the above expression? So we have A here, P2 gas. Okay, so the gas means we would have it in here because we put gases and aqueous solutions inside our Kc, and we do not have a P2 because these are our reactants, these are our products, which means that a P2 would be at the bottom there if it was a gas. At the bottom here if it was a gas, it would be something like this, P2 with no exponent over there, but it is not there even though a gas should be there. We have 3Q2, that is true. We have a 3 over here, we have a Q2, okay, some diatomic molecule, and then that goes to 2PQ3, we have a 2 here, we have our PQ3 over there. That part's looking good. It's just this P2 over here, the fact that it is a gas is not true, because otherwise it would be written in the denominator of our Kc, which means we have B over here where we have 2PQ3L. So it's a liquid. That's also not good for us, but the fact that they have written our products first as a reactant, that is not true, because we have products over reactants, which means this guy should come after the arrows. So therefore this is ruled out because of that. Then we have our P2 gas again, and we have 3Q2 over there. Okay, so they've just swapped them and turned this guy into a liquid, but our products need to come after the double arrows and our reactants first. So the order is wrong over here. And then C over here says 2PQ3. Once again, they are writing the product first where the reactants should be, and therefore that is ruled out as well. Okay, and then D over here says P2S. Well, we've already ruled them all out, so D is our answer, so that's good to know. But the fact that there's a P2S compared to this P2G, that that is very good for us, because in our rice table, there could be a solid, or in this reaction, there could be a solid that we do not put into our Kc over here, which means P2 is a reactant. Reactant comes first at the bottom, but the fact that it is a solid means it is not there. 3Q2, we have our exponent in front, we have our Q2 there. That is a gas, great. Then those are the two reactants that we have on the left of our double arrows. Then we have our double arrows, and then we have our products over here. We have our 2PQ3, and that is a gas, and that is our only product there. And this formatting over here is all correct. So D is our final answer, and that just earned us 2 marks. Okay, we're almost done with question 1, just 2 more questions to go. So 1.9 says, which statement best describes the difference between the end point and the equivalence point in a titration? So this is just terminology. These are definitions as far as an acid and base titration. So we have option A, the end point occurs when the acid or base has completely reacted with each other, while the equivalence point is when the indicator changes color. Then we have B, the equivalence point occurs when the acid or base has completely reacted with each other, while the end point is when the indicator changes color. C says the end point and equivalence point occur at different times and have no connection in titration. And then D says the equivalence point and end point are always exactly the same in every titration. So I'm just going to jump straight to the answer that is correct, and then we can explain why it is correct. So B is the correct answer, and the reason this is true is because the equivalence point is the point where the acid or base has completely reacted with each other. So when the reaction stops because the acids and bases have completely reacted. So this is just a point where the reactants have run out and have reacted in full. But the end point is something visible. It is just something we look at because it is when the indicator changes color. So the end point is just what we see, but the equivalence point is what is happening between the acid and the base. Okay, so that is our final answer there. We don't necessarily have to break down the other options because A is just B, but swapped as far as which definition corresponds with which word. And C and D over there are just aspects that could relate to this, but do not relate to this. So therefore, we just need to understand that the equivalence point is when the reaction has completed, and the end point is what we see because the indicator changes color. So therefore, our final answer is B. So that just earned us 2 marks over there. And then last question, 1.10 over here. A titration experiment was conducted using a sodium hydroxide NaOH standard solution of concentration 0.1 mol.dm to the -3 and a hydrochloric HCl of unknown concentration. In each titration, a volume of 20 centimeters cubed of NaOH was used. The readings from the burette, just the device that we use in a titration reaction, are given in the table below. So we did 3 titrations, all with the same volume of NaOH, but with different volumes of HCl. So titration 1, 2, and 3, and all of these volumes are in centimeters cubed. So what is the concentration in mol.dm to the -3 of the HCl required to neutralize the NaOH? So we have a bunch of options, all very similar to each other. So very similar, and this is a calculation reaction because what we're looking at is some sort of titration. And whenever we look at a titration, we look at our Ca VA over Cb Vb equals Na over Nb formula. We use this formula because this formula has to do with titration. So we can start by just plugging in the values that we have, and then we can see that hopefully the only thing remaining is the concentration of the HCl over here. Our concentration of our acid is what we want, so that is our X over there, and then the volume of it was this and this and this. If ever we're given more than one titration, we have to add them all up and then divide them. So that means our volume of our acid is 26,66 plus 26,50 plus 26,60. Okay, divide that by 3, and in our calculator we can just plug that in, and our final answer is 26,59, and this is in centimeters cubed, and we can always convert this to decimeters cubed because they want it in mol.dm to the -3. But what happens in this equation is that everything is a ratio. So if our volume is in centimeters cubed for our acid and our volume is in centimeters cubed for our base, they will take care of themselves and we do not have to convert them. But if you prefer to always convert your centimeters cubed to decimeters cubed, then you can do that, because we always do need to convert our volume for this formula to decimeters cubed. So that is just something to keep in mind, that in this formula we can use centimeters cubed as long as they are both centimeters cubed, or we can just do the conversion as a good habit to decimeters cubed so that we can keep it consistent in this formula and this formula, because it is also okay for it to be in decimeters cubed in this formula. But right now I'm just going to plug in this answer in centimeters cubed, saying 26,59 over there. So this was the average of all of the volumes of the 3 different titrations of the HCl in centimeters cubed. And then our concentration of our base is 0,1 over there. And then the volume of the base, they told us, was 20 centimeters cubed in all of them. So if we were to add up 20 3 times and divide it by 3, we would still have 20. So we do not have to change that answer, even though we did still take an average of it. And then what this means is that we have the moles of these 2 guys. And they haven't given us an equation, but the moles of these 2 guys are a 1-to-1 ratio. If ever they don't give us an equation, we can try and write one out to see if there is a difference in moles. But if they haven't specified, we usually have a 1-to-1 ratio, which means we're just dealing with 1 on this side, and this is our setup for this equation, which means we can just go ahead and isolate for x here by moving this whole bottom up to this top here and this top here down to this bottom here to keep x by itself at the top. So I'm just going to go ahead and rewrite that for us now. So we have x here, we have our 0,1 times 20 multiplied to the 1 over here. So the 1 just disappears. And then we took the 26,59 down to the bottom here. And then we have x by itself on the left at the top. So then we can just plug this in our calculator and we can see that our answer is 0,0752. And that fits with answer A over here, 0,0752, even though the options are very close to each other, giving us the correct answer of A over there. And that is our final answer, earning us 2 marks for question 1.10 and 20 marks for this whole section. So if organic chemistry is getting a bit confusing at the moment, we're about to break down question 2 here of the June 2025 chemistry paper, where we are going to identify different organic molecules and the questions that they usually ask in this section. Let's jump right in. So question 2 says the letters A to H in the table below represent organic compounds. So we have A, we have C5H12, we have B, we have C4H8O2, we have C, ethyl butanoate, we have D, CH3, CH, CH, CH2, CH3, we have E, butan-1-ol, we have F, we have a structural formula with 1, 2, 3, 4, 5, 6 different C's, and we have our functional group over here on the right. We're not going to break down everything just yet, we just want to see what we have to work with, so when we get to the question that is talking about it, we can then break it down. And then G here, we have 1, 2, 3, 4, 5 C's, but we also have these 2 C's branching off here, so we just need to be mindful of where our longest chain actually is and where our branching chains are, because this guy, if we count this way, we have 1, 2, 3, 4, 5, 6, so that means our branching chain is this guy over here, and then we have a double bond O off of our C in the middle here, and that is our functional group. And then H over here, we have 1, 2, 3, 4 C's, and we have our OH, our functional group, over there. So these are the different organic compounds that we're working with, and then we'll get to each of them as we answer the corresponding question. So 2.1 over here says consider compound H. Is this a primary, secondary, or tertiary alcohol? Okay, explain the answer. So they love this question. I've seen this question in almost every June prelim and final, so it's a very good question to understand. So off the bat, they've told us that this is an alcohol. For 3 marks, we're going to get 1 mark for choosing the correct answer, and then 2 marks for the correct explanation. So that means our OH here is our hydroxyl. Our hydroxyl is our functional group for our alcohol, and that is an OH. How we do approach it, and what is important, is how many C's are attached to the C that the hydroxyl functional group is attached to. So what that means is that this C here is the C that the OH is attached to. And as we can see, there are 2 other C's attached to this C. So that means we're dealing with a secondary alcohol here. So if there was another C here where this H used to live, then we'd have 1 C here, 2 C's here, and 3 C's here. And there would be 3 C's attached to the C that the hydroxyl is attached to. And this would make it tertiary overall because there would be 3 C's. And if we were at this stage where this whole chain didn't exist here and it was just this, we would then have a primary because there's only 1 C attached to the C that the hydroxyl is attached to. So it is all about the carbons that are attached to the carbon that the hydroxyl is attached to and how that all relates, which means we're dealing with a secondary. So 1 mark for writing down secondary over there because there are 2 C atoms attached to the C that the hydroxyl OH is attached to, earning us 3 marks for question 2.1. So then question 2.2 over here, it says write down the letter that represents each of the following. So 2.2.1 says a ketone. Okay, so a ketone is anything ending with an one over there or has a C with an oxygen that is double bonded to it. So we have this ending in one or a C with a double bond on the O. So what we have here are various combinations. We have molecular formulas like this and this. We also have the names of the different organic molecules like C and E over here. We then have a condensed molecular formula for D, where it is similar to the molecular formulas like A and B, but it is just drawn out in a straight line, similar to the structural formulas here. So we have different things to look at when it comes to identifying what might be a ketone. So we have this option if we're looking at a structural formula, and we have this option if we're looking at a name. As we can see when we're approaching the names, this ethyl butanoate doesn't have an one there, so it isn't a ketone. The butan 1-ol also doesn't have an one, so it also isn't a ketone. So that means we need to look for a C double bond O, which means we can look at A, we can look at B. B has an O, so we might have to draw it to see if it isn't a double bond O, but what is helpful to look at is the structural formula so we can see if anything pops out off the bat. So H is an alcohol. They told us that in 2.1. So the questions also help us eliminate which ones aren't the questions that follow. By that I mean we know that it is an alcohol, so therefore 2.2.1, H will not be a ketone as well. As far as process of elimination, we're looking at F or G here, and we have a C double bond O here with our F, but we also have an O and an H coming off of there. And this guy is a different functional group, as we'll see later on, for a carboxylic acid. So that means if we look here at G, we can see that G does have a C double bond O, and this guy is our ketone, which means if we know the answer, we can go straight to the answer, but we're just using a process of elimination to see why it isn't the other ones. Okay, so that means our answer for the first one, and the reason we do not have to draw B is because we see G, and therefore our answer for the first one is G. So that just earned us 1 mark over there. And then 2.2.2 says a molecular formula. So a molecular formula of a hydrocarbon. So off the bat, we can rule out G and H because we've already identified them, and we know they aren't hydrocarbons by themselves, just having C's and H's. But we also know that they aren't molecular formula because these guys are structural formula over here, G, H, and F. So we have our names for E and C, but these guys also aren't hydrocarbons, having just C's and H's, which means we're looking at either D, B, or A over here. So B over here can't work because it has an O, so it is not just C's and H's. And then D is not a molecular formula. D is a condensed molecular formula, and that is not what they want. So therefore, our answer has to be A here, but we have C5H12 because they are just C's, they are just H's, and it is in a molecular formula structure. So we had G for the previous one, and we have A for 2.2.2, earning us 1 mark over there. So then 2.2.3 says a reactant in the preparation of compound C. So compound C, we have an ethyl butanoate. If we saw the previous video, we were talking about esters. So this is an ester that we're dealing with, and esters are made from an alcohol and a carboxylic acid. The yle came from the ol for an alcohol, okay? And the butanoate came from the oic for butanoic acid. So what we need to look for is either an ethanol, because we have meth-eth, so we have an ethanol for our alcohol that made the ethyl part of the ester, or we need a butanoic acid to make up the butanoate for our ester. So that means we can look for any acids off the bat, so we can see if there are any acids that we're dealing with. H is an alcohol, G is a ketone, so F here, this is a carboxylic acid. We just need to count, are there the correct amount of C's, and if so, then this could be the reactant in preparation of compound C. So we have meth, eth, prop, bute, pent, and then we also have hex. Okay, so hex is too many. That is more than our bute, more than our 4. A reminder that meth is 1, eth is 2, prop is 3, bute is 4, pent is 5, hex is 6, hept is 7, oct is 8, non is 9, and dec is 10. Okay, they only usually ask up to about 6, so we don't really need to know 7, 8, 9, and 10 as much, but it helps to know all of them just in case they do ask. But at this stage, we can see that this guy has 6 C's, which is more than the 4 C's needed for our butanoate. So F is out, which means we need to look for some sort of alcohol then, because I don't see any other carboxylic acids. So here we have an alcohol, so we'll look at that. The fact that there's an O here means this guy could be an alcohol. We just need to see how it is once we draw it. Okay, D does not have any O's, so it cannot be an alcohol, and A also does not have any O's, so it cannot be an alcohol, which means we're looking at either B or E here, because those are the only other 2 with O's in them, and we haven't identified which group B is in. So let's check butan 1-ol first. Let's check out E. So the fact that we need an ethanol in order to create our ethyl here, this butan 1-ol has 4 C's, which means it is not the same, because butan 1-ol doesn't become the butanoate here. The butan and the butan match, but the alcohol doesn't turn into the oic acid. The alcohol turns into the yle. So that means that our chain is too long for E in order to actually be the reactant for the alcohol for our ester over here, because butan 1-ol is not going to become the ethyl. It'll become butyl, and that is not what we want. So therefore E is out. So our answer is B, because that is the only other option we have, but we are going to quickly draw it to see that it does fit what we want here. The reason that it is B, and as I was drawing it, we cannot draw it as an alcohol because there are too many O's. Usually for an alcohol there would be an OH in our molecular formula. So that means when we draw this, we're going to see that this is actually an ester as well. So this is a bit of a different formatting, and we don't see this too often. So usually we look at just an alcohol or just a carboxylic acid. But in this case, we see that this is ethyl ethanoate, and they're using this whole carboxylic acid, a portion of it, the ethyl, to break off with a butanoic acid somewhere in order to form the ethyl for this ethyl butanoate. So when we draw it, we'll have a C here, a C here, we have an O in the middle, we have a C here, and a C here. We then have our double bond O on the ethanoic acid portion of it, and then from there we can construct all our C's. Right now we've dealt with the 2 O's, we've dealt with the 4 C's, and that means the remaining slots are all going to be filled up by H's, and this is what we're dealing with. This will be our ethyl, splitting up our O in the middle. This will also come up later for another ester question. So we have an ethyl over here, and then this is our ethanoate. And the way that I like to remember the ethanoate is make a double bond off of the O over there and add the C, and that is just how I remember that. The ethanoate gets the double bond on the O for this portion. But then once again, weird formatting, we are dealing with the ethyl over here that joins the ethyl from another butanoic acid. So this will react with butanoic acid, and then the ethyl will join the butanoic acid. So that is just a different formatting, and that is why B over here works as a reactant in the preparation of compound C. So that just earned us 1 mark over there. So then 2.3 says write down the structural formula of 2.3.1 compound D for 2 marks. Okay, so compound D over here, this is currently in a condensed molecular formula, and we need to write the structural formula of it. So that means we have to draw it something like F, H, or G. Okay, so off the bat, we do not see anything in brackets here. Say now this guy was in brackets, for example. That means that would be a side chain and not on the main chain. That means we'd have to look at some sort of attachment like this C over here, for example, or something that is not in a perfectly straight line. But there are not any brackets over here, which means this is all on a straight line. So what we can deal with is just write down all the C's in one straight line, and then we can get the corresponding H's and see if there are any double bonds or triple bonds as well, or if there are just single bonds throughout. So we have 1, 2, 3, 4, 5 C's over here, and then they are telling us how many H's are branching off of each one. 3 H's coming off of this first C over there, 1, 2, 3 H's. In a test, draw all your H's. For now, I'm just going to draw the lines around them. Then this second C only has 1 H there, so that means we have to deal with something else. This next C also has only one H over there. And the fact that there's only one H over there for both means that these guys would usually have two H's, and they don't in this case from what they've told us, which means there has to be a double bond here so that they each have 4 lines around them. Because right now this guy has 1, 2, 3, 4. This C over here has 1, 2, 3, 4. Happy days. This C over here has 1, 2, 3, 4. So it is also satisfied. So the only way we could make that work is by putting a double bond in between here. And then at this stage we are on this C. This C has 2 H's branching off of it. Okay, this guy is happy. 1, 2, 3, 4 over there. And then this last C has 3 H's just like the first C, which means it is normal just like that guy. So we have 1, 2, 3 H's branching off, and this has 4 lines around it. So it is happy. So right now we just earned 2 marks because we drew the structural formula of compound D and accounted for the fact that there is a double bond on the second C. Okay, and then 2.3.2 says the functional group of compound F. So compound F is here. When we were identifying things earlier, we saw that this was a carboxylic acid, and before that we identified that this was the functional group. So they want us to draw the structural formula, not of the whole compound, but of the functional group itself. So that means we can just go ahead and draw what we've put a square around here. So we have our line, we have our C, we have our double bond, we have our O, and we have our H. The way that we know we are just drawing that, when we talk about the functional group, that is just the specific key that we attach to the organic molecule to identify which group it fits in. Okay, which means that we see a C and an O and an O and an H, some type of Q like this, we know that we're dealing with a carboxylic acid. And that means we have to look for the grouping of COOH wherever it is grouped in this. And it is usually at the end, but we can identify it, and then all they want is for us to draw that. So that just earned us 2 marks over there. And then 2.3.3, the functional isomer of compound G with a prefix of 4-methyl. So another 2-mark question, drawing the structural formula, and they want the functional isomer. So we have 3 different type of isomers. We have structural, we have positional, and we have functional. Okay, so if we have a functional isomer, it means we need to change the functional group, change what combination of key we're working with in order to make it sit and fit in another group. So we are looking at G over here, and earlier we identified that G is a ketone, but now we want to change it so that it is not a ketone with a very specific prefix of 4-methyl. So a functional isomer of a ketone is an aldehyde. Those guys are just a pair that we need to look at. They are very common ones that we work with, just like another common functional isomer group pairing that they work with is a carboxylic acid and an ester, because a carboxylic acid is a Q, but an ester is a COO, like that, which means these two are usually functional isomers that we have to look for. And then the other most common one that we're working with now is a ketone, and turning the ketone into an aldehyde. So we turn it from an one to an L, and that means we turn it from a C double bond O to a CHO, and the aldehyde always moves to the end of the chain. So off the bat, they want us to start with a prefix of 4-methyl, because the 4-methyl means that we have our C branching off in the beginning, which, coming back to what we were talking about earlier, the fact this C and this C are grouped like this, we think for a second that it is an ethyl branching off here, where we have a methyl would just be 1 C branching off, and then ethyl would be 2 C's stacked on each other branching off. But if we were to draw it a bit differently, something like this, for example, getting rid of that guy, we would see that our longest chain is in fact bent, and it is not the straight line over here, because we have 1, 2, 3, 4, 5, 6 C's over there, and we only have 1, 2, 3, 4, 5 C's over there. So we don't have a chain with 5 and an ethyl branching off there. What we have is 6 over here and a methyl branching off here. And as we can see, 1, 2, 3, 4, the 4-methyl is what we're dealing with here. So this was actually a clue and something to help us orient ourselves as to where our longest line actually is. So that means if it is a functional isomer, it has the same amount of C's and H's, but now we are no longer dealing with a C double bond O, we are moving it and changing it to a CHO at the end, which just means we are moving our double bond over here to the end, and because of where it is located, it means there's also a space for an H to live on there. So the main thing we look for is that a ketone is a double bond O in the middle, and an aldehyde is a double bond O on one of the ends, because that leaves us availability to have one of the H's attached to that C as well, which means it is exactly the same. We have 1, 2, 3, 4, 5, 6 C's over there, and that dealt with 1, 2, 3, 4, 5, 6 over there. Cool. And then on 4, 1, 2, 3, 4, they said we have a C branching off, because that was our 4-methyl that we were talking about over here, and that they told us was the prefix for this whole naming convention. And that means we've dealt with almost everything. We just need to move our double bond O to the beginning, which means we have our double bond O here, and that means we have one availability for another H over there. And that is why this aldehyde is a CHO, because of where it is located compared to our ketone, where our double bond O is in the middle, and there's 1, 2, 3, 4. There's no other space for any H's to live there, which means at this stage we have moved our double bond O, changing our functional group. We have the correct side chain branching off of it, and we have the correct long chain, which means we can just add the H's everywhere that there's availability, so that there are 4 lines around all the C's, and then we can go ahead and count that it is all the same. But at this stage it should correspond, and we will have the functional isomer of compound G with a prefix of 4-methyl, changing the functional group, keeping the C's and H's the same amount, and having the correct branching of the side chain there. Okay, and now we just earn us 2 marks. A reminder, just draw your H's in the test, but for now we are just checking the general structure and that it all adds up. Okay, so we're on 2.4 here. It says write down the IUPAC name of 2.4.1 compound D. So 2 marks over there, and that's quite nice because we already drew the structural formula of compound D being this guy over here, which makes it a lot easier for us to name it once we can see it in the structural formula. So if they hadn't asked us to draw the structural formula, it would always be good practice to draw the structural formula first and then name it accordingly. But right now we have our structural formula over here where we have 5 C's and we have our double bond C on the middle. So we're dealing with some sort of hydrocarbon chain, and we just have C's and H's, and we have a double bond. So an ane is a single bond, ene is a double bond, ine is a triple bond. So that means we're working with this guy over there. So that means we have meth, eth, prop, but, pent. So we have our pent over there, and then we have a line, because what is important is where the double bond is. And if we count from left to right, we have 1, 2, 3, 4, 5, and that means it's on 2. And if we count from this way, from right to left, we have 1, 2, 3, 4, 5, and that means it's on 3. We always have to take the double bond to the closest side that we can start with, which means we're counting from left to right, and we have 1, 2, and it is on 2. So we have pent 2, and then over here we're working with this part, meaning a double bond, and then that is pent 2 ene, and that is our final answer for the IUPAC name of compound D over there. Okay, so we just earned 2 marks. And then 2.4.2, write down the IUPAC name of compound G for 3 marks. So we've also looked at the functional isomer of compound G. We drew that over here. Now we need to write the IUPAC name of the original, not this guy over here. But they did help us a little bit, again, with the prefix of 4-methyl, because if we are identifying our longest chain, we have a 1, 2, 3 over there. The reason we're counting from right to left is because our functional group is closest to this side. If we were to count this way, we'd have 1, 2, 3, 4, and that is not what we want, just like we were talking about for compound D, the previous question. So that means we have 1, 2, 3, 4, 5, and then 6 is over there. A reminder that we scratched out the CH3 and just drew it so we could identify the longest chain a bit easier instead of the weird formatting that they gave us to work with. So that means we have 1 to 6 like this, and that means branching off of our 4, we have our methyl over there, just like the prefix they were talking about here. So we have 4-methyl over there. We always write that first. We write any side chains first. So we have this C dealt with, and then we have our longest chain of 6. So we have hex hexan. And the reason we stop and don't just say hexanone is because we have our functional group located on the third C in our longest chain, which means we add a 3 first because that is where our functional group is located. And then we add our own because it is a ketone. A reminder that in 2.2.1, we identified that G is a ketone. So we knew that we were working with a ketone the whole time. It always helps to see which question related to which organic molecule. So we can reference those questions in later questions about the same organic compound. But that means we're dealing with 4-methyl. We have our side chain correctly identified in the beginning. We have hexan, the fact that it is 6. We've identified our longest chain. And then we have our 3 coming off of there because that is the correct numbering for where our functional group lives, getting priority in the numbering. And then own over here just has to do with the fact that that is the suffix that we're working with when we're working with a ketone. So that just earned us 3 marks over there. And then 2.5 says consider compounds E and H. So E was over here. It was our butane butan 1-ol, and then H over here is our other alcohol. So we are comparing two alcohols, one alcohol ending in OL, that is our hydroxyl, and another one with an OH, that is also our hydroxyl. So we are comparing two different alcohols, E and H. So 2.5.1 says identify the type of isomer. So the fact that we know it is an alcohol because it has an OL or an OH, even though one is written as its name and the other is a structural formula. So we know we're dealing with alcohols. So the next thing to look at is, do we have the same length in each chain? We have meth, eth, prop, but, so that means 4. And here we have meth, eth, prop, but. So we also have 4 over there. This is why they can be isomers, because they have the same amount of C's and H's, but just something different about them. And the 3 options we have is a functional isomer, but it can't be because they have the same functional group. So that's ruled out. Then the other option is a structural isomer, which means we'll have some sort of side chain where there's a C branching off here, for example, erasing this guy. And then we have a methyl attached there instead of just the long chain with just carbons. So it won't just be butan 2-ol in this case. It'll be 2-methyl-propan 1-ol, which means we add a side chain and we mess with the configuration of the long chain. So that is the second option where we are looking at the structural. Okay, but we do not have that. We do not have any side chains. We have the same long main chain length, which means the only other option, if it's not functional, it's not structural, means it has to be positional. Positional means the functional group is the same, the long main chain length is the same, which just means we have moved the location that the functional group is going to be on. Because right now our functional group for E is on 1, but our functional group for H is on 2 over here. It is on the second C. So if we were to name this, it would be meth, eth, prop, but, butan 2-ol. And that is what we're working with over here, a positional isomer. So if we just write positional over there for 2.5.1, we will earn ourselves 1 mark. And then 2.5.2 says define this type of isomer for 2 marks. So that has to do with our thinking that we previously had, where it isn't a functional isomer, it isn't a structural isomer, it is a positional, which means all we've done is we've changed the location of the functional group. Okay, and our definition for that is it has the same molecular formula, but different positions of the side chain substituents or functional group on the parent chain. Okay, so this definition, same molecular formula, but different positions of the functional group on the parent chain. So we identified that all we did was move the functional group location. That earned us 1 mark for 2.5.1. And this definition here of same molecular formula, but different positions of the functional group on the parent chain, which has earned us 2 marks over there. And then 2.6 over here, last question of this section, says consider compound C. So compound C is our ethyl butanoate that we were talking about earlier. And 2.6.1 says, to which homologous series does compound C belong? So we were chatting about this and we identified that it is an ester. We needed to understand this for 2.2.3 when we were looking at a reactant in preparation of this ester. So 2.6.1, to which homologous series does compound C belong? It belongs to esters. So we just write ester over there and we earned 1 mark. So then 2.6.2 says, give the name of the catalyst required in preparation of compound C. So this is just a theory question, something we have to know. There are certain conditions for certain reactions in order to take place, but a common catalyst that we use for a lot of them is concentrated sulfuric acid. We gave the name. If we wrote H2SO4 for the answer, we would not get the mark because they only wanted the name, not the molecular formula. And we just earned 1 mark over there. And then 2.6.3 says draw the structural formula of compound C. Okay, so we broke this down when we were looking at 2.2.3 to see why B, also an ester, was one of the reactants for C. We'll break it down again where we have an ethyl butanoate. So ethyl means we have 2 C's over there, and then we always have to connect these 2 parts, the aryl and the O8, by the oxygen over there. And then what helps to orient ourselves is drawing a dotted line down the middle of an O to see which side the aryl lives and the O8 lives. Okay, which means we're then dealing with a butanoate on this side. So we have meth, eth, prop, but. So So we have our O over here. Then a reminder for an ester, our functional group is a COO. It is not the COOH, that is our carboxylic acid, one of the reactants that make an ester, but it is the COO, which means we have a C and an O, but now we need one more O in order to satisfy the structural formula. So we have an ethyl and a butanoate. And the ethyl came from our alcohol over here, and that is meth, our ethyl over here. But then the butanoate, and a nice way that I like to remember it, is that it has an O over there, which means we can draw a double bond and draw our C coming off of it, which means our double bond with our O is always on our O8 attachment. And here we have our meth, prop, but. So this is our butanoate, which means on this first C next to this O over here is where we need to attach our double bond O, because then we have a COO, and this forms our functional group right in the middle to make this an ester. So we have the right amount of C's for our aisle on the left. We have our O splitting up the naming so that we can just identify which parts on the left and the right of the O relate to the aisle and the O8. And then at this stage, we had 4 C's here, and we just know that our O8 has an O in the name over there, and that is where our double bond has to be. So we are going to take the double bond off of our C, add the O over there, and then we have our COO, our Q, our functional group for our ester. At this stage, we're done. We just need to add the H's correctly. And this would be our final answer as the correct structural formula of compound C, our ethyl butanoate. Here's our ethyl, and here's our butanoate. And right here in the middle is our functional group, our Q over there. And that just earned us 3 marks over there and 25 marks for this whole section. So if boiling point is getting a bit confusing at this stage, we're about to break down question 3 here of the June 2025 chemistry paper, where we're going to look at the standard form as well as break down the usual structure that they have in the June prelims and finals. Let's jump right in. So it says the factors that affect the vapor pressure of different organic compounds are investigated. The table below shows the vapor pressure of 5 organic compounds represented by the letters A to E. Okay, so we have our organic compounds down here, our molecular mass of each of them over there, and then the vapor pressure of them over there. So we have propane for A, for B we have butane, C we have ethyl methanoate, D we have alcohol, and E we have propanoic acid. So usually they're just testing a 1-to-1. By that I mean they're either testing how chain length affects boiling point, or the type of bond, or the bond order. In prelims and finals specifically, they're just testing a 1-to-1, how chain length affects boiling point, how type of bond affects boiling point, or how bond order affects boiling point. What this means is that they don't usually mix them all up like this. Right now we have a mixture of different things that are in the same homologous series, things with different functional groups, and then things that might be different lengths. But that means when it comes to a mixture like this, they're just going to compare specific ones in this list and not compare all of them in one go. Okay, one thing to note is that chain length is how long a chain is. So it is the amount of surface area, something like this, for example, versus something with 5 C's. Okay, this guy has the longer chain length. Or if we had something like this and they had the same amount of C's, this guy would still have the longest chain length. Surface area is dictated by the longest chain length, not any branched chains, because these little arms, these little C's branching off are weaker and therefore easier to snap off, which means there's less energy required in order to overcome the intermolecular forces. So that is chain length. Type of bond has to do with the functional groups that they have, because different functional groups will determine the type of bond of the organic compound, which means alcohol, for example, will have a hydroxyl and therefore a hydrogen bond. Others will have mixtures of dipole-dipole or just weak London. And a reminder that our electronegativity for our London, our dipole-dipole, and our hydrogen are in the following ranges. So when we have our electronegativity that we'll look for on our periodic table, weak London is when we subtract, say now, our C from our H. If we go to our periodic table, we'll subtract the electronegativities of the thing on the right compared to the thing on the left, meaning that if we take our electronegativity here of C with 2.5 and subtract H from it, 2.1, we have a 0.4. And that means most hydrocarbons just end up being in weak London, because our range for weak London is 0 to 0.4. 0.4. So anything in between or including one of these numbers is weak London. We then take it a step further with dipole-dipole, which has a range of 0.5 to 1.4. And that'll be most haloalkanes, where we have a halogen on our hydrocarbon chain, as well as an ester, for example. And then last one is hydrogen bonds, or H bonds, and that is from 1.5 to 2.1. And the way that we remember hydrogen bonds is HNOF, where we have a hydrogen with a nitrogen, an oxygen, or a fluorine, for example. So we have an H over here, we have our N, we have our O, we have our F. So that means that'll be our hydrogen bond, and usually that'll include alcohols and carboxylic acids. So that'll be type of bond determined by the functional group. And then we have our bond order. This is the last thing. It is the least important. The most important is type of bond. That happens first. Chain length is what we rank second, and then bond order is what we rank third. And bond order is a single bond versus a double bond versus a triple bond. We will look at that when that comes up, but single bonds are longer and by themselves, double bonds are shorter and stacked, and triple bonds are the shortest and the most stacked, which means they are the hardest to break, because it's like we have three different bridges linking between them in order to break. Okay, which means they're shorter, closest to each other, and hardest to break compared to double and single, which is just one bridge to break down, and therefore it is less reinforced. This is something also to keep in mind when we look at bond order, if they are just comparing the exact same chain length and the exact same type of bond, and the only difference is whether one has a single bond or a double bond. If this was a propane compared to a propene, for example. Okay, and with that information, this is how they would structure each question. And in this case, we have a mixture of different chain lengths, different types of bonds, and different bond orders that we are about to compare in different combinations throughout. Okay, so then 3.1 over here says define the term vapor pressure. So 2 marks for the definition. It is an all or nothing question. This is just something to learn on our definition sheet. So vapor pressure is the pressure exerted by a vapor at equilibrium with its liquid in a closed system. So that just earned us 2 marks over there, and this is a weird combination of words. But what this means is that if we are in a closed system, a beaker like this, we have a liquid that evaporates into little gas molecules, but at the same time these little gas molecules are also condensing and forming liquid again, and they are in equilibrium at the same rate in this same closed system. So that is just a little explanation to help ground this definition. But what is important is the application of vapor pressure, because linking back to all of this whole section is about boiling point. And what we know about boiling point and what we're about to break down is that boiling point is inversely proportional to vapor pressure. They are not the same. So if something has a higher vapor pressure, it means it has a lower boiling point. But if something has a lower vapor pressure, it means it has a higher boiling point. A nice way that I like to remember this and that I teach my students is if we have a bottle in a car, don't know if you've ever seen this before, but if we have a bottle in a car, let's say now we have 4 little particles in there. And if you leave this bottle in a hot car, the bottle ends up expanding. Okay, so that means our volume has increased. So our boiling point has increased, and therefore our volume has increased because our plastic bottle has expanded in the hot car. And then what happens is that these 4 little dots, that's how many dots we had in both of these, there is more space for them to bounce around, which means there is less pressure because they are hitting each other less, which means our VP or our vapor pressure goes down. Because our boiling point has gone up, our plastic has expanded because it is in a hot car. The volume of the container it is in has expanded, and because of this there's less pressure because they can bounce around more and they are less likely to hit one another compared to this example over here, which means there is more space to bounce around and therefore less pressure. So this is just a nice way to think about it, especially in question 3 here, where that is the relationship that we're working with. So 3.1, we defined the term vapor pressure for 2 marks, an all or nothing question, and we got our 2 marks there. And then 3.2 here says write down the homologous series to which compounds A and compound B belong. So this is a 1 mark question. This is theory and understanding, and what we can see is that A is propane and B is butane, which means they do belong to the same homologous series, and they both end in ane over here, not ene or ine, which means we are dealing with an alkane alkane. This is just something we need to know and learn to identify, which means we have an alkane because it ends in an ane, and that is 1 mark. Our homologous series for this is not a hydrocarbon. That is just the heading for the whole section when we start to reference alkanes, alkenes, and alkynes, but alkane is the homologous series, which means we have identified them. And then 3.3 says explain the decrease in vapor pressure from compound A to compound B as indicated in the table. So as we can see, propane has a higher vapor pressure and butane has a lower vapor pressure. So propane looks something like this: meth, eth, prop. So we have 3 of them. So this is our prop. And butane looks something like this, where we have meth, eth, prop, but. We have all our H's going around, and then what we can see is that the vapor pressure is lower for butane. And this makes sense based on our previous understanding because the boiling point is higher, and boiling point and vapor pressure are inversely proportional. So they love this question, and we'll see that 3.3 and 3.4.3 have exactly the same format as to how we answer this question. So what we need to start with is that compound B has a longer chain length, which is what we mentioned in the beginning. We are either comparing chain length, bond type, or bond order. And as we can see, if they are in the same homologous series, the only thing that we are comparing is the fact that this is a longer chain than this guy. There are no double bonds over there or anything like that. They also aren't different functional groups, which means we are just dealing with the chain length here and comparing it a 1-to-1. How chain length affects boiling point, and then our last link in the chain is that vapor pressure is inversely proportional to boiling point. But now that we have compound B has a longer chain length, we always have to talk about the intermolecular forces. The forces between, say now there were 2 of these guys with their H's over there as well. The forces between this H and that C, for example, intermolecular, in between 2 different molecules if they were in the same beaker, for example. So we always have to mention intermolecular forces when it comes to this. So that means, as we can see, we only have C's and H's. And like we were talking about earlier, if we go to our periodic table, C minus H, 2.5 minus 2.1 placed us in the weak London range. That is what we had when we were checking the electronegativity, and there are only C's and H's, which means we end up being 0.4 being weak London, which means they both have weak London, so we have to write that. Both have weak London forces, but because this has a longer chain length, there are more intermolecular forces to overcome. This guy only has 3 on its main chain, which means there's less interaction between the H's and the C's in 2 different molecules. But because these guys are longer, therefore there are more H's interacting with the C's here, which means they have stronger intermolecular forces, and that is what we write. But B has stronger intermolecular forces, so that just earned us 2 marks over there. And then our last link in the chain is always saying more energy needed to overcome the intermolecular forces in compound B, and that would earn us 3 marks over here. And the reason this all adds up is because more energy means higher boiling point. So if we have more energy needed to overcome our butane, means we have a higher boiling point because there's more energy required in order for these guys to start breaking up, okay? And because there is a higher boiling point, there is a lower vapor pressure. And those are the last 2 points in our conclusion that we can write down should we need to, but based on the mark allocation, it's only 3 marks, which means 3 points, which means we can leave out the boiling point portion and the vapor pressure portion, but you can always write that down to finish your conclusion strong. And we just earned 3 marks. And then 3.4 over here says compounds C and E are functional isomers. 3.4.1 says define molecular formula. So this is just a definition on our definition sheet, and molecular formula is a chemical formula that indicates the element and numbers of each of the atoms in a molecule. So this is also an all or nothing question, and we just earned 2 marks over there. But a molecular formula is something like C3H8, for example. It is this grouping where we can see the amount of each of the atoms in the molecule. So this is just something to keep in mind, and one of the definitions on our definition sheet. And with that, we have 3.4.2, which says which compound will have a higher boiling point between C and E. So we got C, we have E, and C is ethyl methanoate, and E is propanoic acid. But a higher boiling point for 1 mark, which will just help us orient ourselves in 3.4.3, is just what we were talking about earlier, where we just have to interpret the difference between boiling point and vapor pressure. So if we're looking at C, C has a higher vapor pressure and E has a lower vapor pressure, which means the one with a higher boiling point is the one with the lowest vapor pressure, because vapor pressure, if that is lower, our boiling point is higher. So this is just an interpretation, and if we write down compound E, we will get our 1 mark over there. And we can either write down compound E or propanoic acid. Both options are good on the memo. And then 3.4.3, very similar to 3.3, says explain the answer to question 3.4.2. Why compound E, the propanoic acid, has a higher boiling point. So this one is just a 4-mark question compared to a 3-mark question, but the formatting is very much the same, which means we just need to look at a couple things. So C and E are functional isomers as they mentioned, which means they have the same amount of C's and H's, which means they are the same chain length, which means we aren't dealing with chain length. So that is ruled out. And then we also aren't dealing with bond order because they both have a double bond with a C and the O, because our ethyl methanoate has a Q like that, and there's a C with a double bond O over there. And then our propanoic acid is our COOH, and we also have our C double bond O over there, which means they both have the same bond order as well. So that isn't what we're comparing, which means the thing when it comes to functional isomers specifically is the type of bond. And this is based on the fact that this guy has a Q only. So ethyl methanoate looks like this. So we have meth, eth, then we have our O over there, and then we have methanoate, which means we have our C coming off there. And then we have our H's all around, and then just one more H over here. So this is our ethyl on this side, and this is our methanoate on this side, with the double bond O on the C is where we get it when we split up our ester. So we have our ethyl methanoate, and then our propanoic acid, very similar. We just have meth, eth, prop, and then we have our double bond O, and then an O and an H. And this is where our Q lives, our COOH over there, and this guy is where our COO lives, this portion over here. And this is our propanoic acid, which means we have our Q over there. So the fact that they are functional isomers, they both have the same amount of C's and H's, they both have the same bond order, both have a double bond O on the C. The only difference is the fact that this guy has a hydrogen bond over here, compared to these guys, which only have a C minus a O, leaves us in what electronegativity? C minus O, 3.5 minus 2.5 leaves us with a dipole-dipole, because that leaves us in 1, and anything from 0.5 to 1.4 is our dipole-dipole, which means these guys, because of the C's and the O's and no H's attached directly to the O, because remember that is what a hydrogen bond is. It is an H directly attached to an N, an O, or an F. And we cannot interpret this H and that O as a hydrogen bond. So the fact that this has dipole-dipole and this has a hydrogen bond means this guy requires more energy to overcome the intermolecular forces and therefore has a higher boiling point. And that is what we're dealing with here, because we see it is a lower vapor pressure, which means it has to have a higher boiling point. And then this is the reason, because it is the type of bond it has based on the fact that it has a Q with an H, not a Q without an H, and this hydrogen bond increases its boiling point. So that means we can just continue from where we left off with 3.4.2, saying compound E. Compound E has a hydrogen H bond. Just write hydrogen bond in the test. But then for our second mark is talking about what intermolecular forces ethyl methanoate has. And as we saw when we subtracted 2.5 from 3.5, is that it landed in the range of dipole-dipole, sitting with an electronegativity of 1, which means we just have to write compound C has dipole-dipole. So that just earned us 2 marks, and now the formatting is exactly the same as question 3.3 over here, where we just have to say compound E has stronger intermolecular forces than compound C. And that was our 3rd mark. And then our 4th mark is once again saying more energy required to overcome intermolecular forces in compound E. Cool. And those 4 points just earned us 4 marks over here, where we stated the intermolecular forces of compound E, then that of compound C, then compared the intermolecular forces as to which one was stronger. And because there was more energy required to overcome these intermolecular forces, it has a higher boiling point relating to this. And we could interpret this on the table, seeing that if there's a higher boiling point, there is a lower vapor pressure, as we can see here for the propanoic acid. Okay, so 3.5 over here, quite a nice question, a grade 11 empirical formula, provided we remember the usual formatting for this, worth 4 marks over here. So 3.5 says the percentage composition of some of the elements in compound D is given as 61% carbon and 11.86% hydrogen. Determine with calculations the empirical formula of compound D. So as we can see, compound D here just says alcohol. It doesn't say what type of alcohol it is. That is the reason that they wrote it like that, because we are now working out its empirical formula. Okay, which means our usual setup is carbon, hydrogen, and what is something to keep in mind here is that this is an alcohol, right? Which means it has an OH, it has a hydroxyl group, which means we also have to add an O here because there would be an O in this empirical formula. Okay, we just need to keep that in mind because if we forgot the O, we would get the wrong answer. But now we know which elements are in our alcohol, and we remember the O was there based on the fact that it has a hydroxyl, an OH over here, which means we can start plotting because it says it has 61% carbon, which means we can just turn it into grams, which means we have 61 grams over here because we are treating it as a whole compared to 100. And then it has 11.86% hydrogen, so we can write 11.86 grams, and then oxygen will be the rest. So on our calculator, we can just go 100 minus 61 minus 11.86, and then our answer for that is 27,14 grams. At this stage, in order to determine the empirical formula, we have to get everything to moles. And the way that we get things to moles once we have the grams of something is to write N equals M over capital M. And then we do the same thing here and the same thing here. The reason we do this is because we have grams, our little m at the top, and then we have the molar mass that we can always get on our periodic table, which means carbon is 61 is the amount of the actual grams we have here. Then our molar mass is on our periodic table. That is 12 over here. So we have 12 there. And then hydrogen is 11,86 for its actual mass, and its molar mass is just 1, as we can see here on the periodic table. And then our oxygen is 27,14 is the amount in grams that we have, and then its molar mass is just 16. Even though it is a diatomic molecule, we do not treat it as such, same as hydrogen over here. We just put the 16 as if it was just one atom of oxygen. So then we write 16 over there. And then from there, we're going to plug each of these into our calculator, and we're going to get answers that we can round off to 2 decimal places. Okay, so 61 divided by 12 is 5,08, and then 11,86 divided by 1 is the same thing. So we have 11,86 over there, and then 27,14 divided by 16 is 1,70 over there, which means we have these answers that have decimals, and we can't just plug in C5,08 over there. That isn't how we write numbers in our empirical formula. So that means we have to divide each of these numbers by the smallest number that we have here, and the smallest number that we have here is the 1,70, so that we can get a ratio, so we can plug in these rounded numbers into our molecule to get our formula, which means we have divide by 1,70 there and divide by 1,70 over there, which means our rounded answers are 5,08 divided by 1,70, and we have 2,99, which means we can round that up to 3. It is close enough. 11,86 divided by 1,70 is 6,98 as well, which means we can round that up to 7, and then 1,70 divided by 1,70 is just 1. And all of these were close enough to round up to whole numbers. None of them were 1.5s, for example, where we would then have to multiply everything by 2 in order to get them as round whole numbers, which means we can write our final answer in the order that we have of CHO, and that means we have C3H7, and then O is just 1 over there, so we don't have to write the 1. And this is our final answer for our empirical formula for this alcohol compound D, and that just earned us 4 marks over there. And then last question, 3.6 over here, says write a balanced equation using molecular formula for a complete combustion of compound A. So compound A over here is our propane. So our propane is meth, eth, prop like that, and then we have our H's all around like this. And it just helps to draw it so that we have the structural formula, so we can then count the amount of C's and the amount of H's that we have for our molecular formula, as they mentioned over here. So a complete combustion means that it takes place in the presence of oxygen. And if it takes place in the presence of oxygen, it means it releases CO2 and water. To life science students, this is very similar to respiration because the fire is breathing. If we don't do life sciences, then this is just something we have to know. So if we blow on the fire, it increases and grows. And that is because it is using up the oxygen, creating CO2, and then releasing water as well, which means we are dealing with compound A. We are dealing with the propane that we just drew, which means we have 1, 2, 3 C's. So we have C3, then we have 1, 2, 3, 4, 5, 6, 7, 8. 8 H's over there. So we have C3H8 plus O2 because the lighting of this propane is taking place in the presence of oxygen. So that means we have our plus O2 on our reactant side, and then this goes to CO2 that gets released because the oxygen is burning up, and these C's are joining some of these O2s and forming CO2. And then we also add water because water gets released when this gets burnt. If we were to hold this under a test tube, we would see little water droplets in our test tube, which means we knew that compound A was this in terms of molecular formula, and we knew the other reactant, which was oxygen, and the two products for a complete combustion reaction, which are CO2 and H2O, which means we're almost done. We just haven't balanced this equation. So once we do that, then we'll be done with this question. So a good method is to draw a line down the middle of your arrow so you can see what's happening on the left side and what's happening on the right side. I'm sure a lot of your teachers have taught you this method. Then you write the C over there, the H over there, and the O over there. And then on this side, you write the C, the H, and the O in line so that we can keep track of how much we have on the left side and how much we have on the right side of each of these atoms. So C, we have 3 C's over here, we have 8 H's over there, and then we have 2 O's over there. And then here we have 1 C, then we have 2 H's over there, and we have 3 O's overall because we have 2 here and 1 here. So H's and O's usually take care of themselves. So the best thing to balance first is the amount of C's, which means we can add a 3 in front of our CO2 and then just update our numbers here now because we have 3 C's. 3 multiplied by 1 is 3 over there for our C's, and then for our oxygens we have 3 multiplied by 2 is 6, and then we have to add this O over here, which means we have 7 over there. So we have 7 O's now. Okay, so at this stage our C's are balanced, and then we need to balance our H's and our O's. And if we try and balance our H's, our O's will probably take care of themselves. So on this side we need to update our amount of H's, and our H2O, there are 2 hydrogens in our water molecule over here, which means we have to put a 4 in front of here in order to balance our H's, because 4 times 2 gives us 8 over there. And then that means we have H8 over here, and then 4 multiplied by 2 is 8 as well. So that is sorted. We just need to double check the amount of O's we have on our right side now, because this 4 also multiplies to this O over here. So that means 3 multiplied by 2 is 6, and then we have to add 4 multiplied by 1, and that is 4. So we have 10 O's over here because we multiply in each molecule and then we add up across molecules. Okay, so 3 times 2 is 6, and then 4 times 1 is 4, so 6 plus 4 is 10 over there, which makes our last move quite easy because we have an oxygen by itself on the left side, which means we can just go ahead, add a 5 in front of there because there are no other oxygens here, which means 5 multiplied by 2 is 10, and now our oxygens are balanced as well. Cool, and that means our carbons, hydrogens, and oxygens are all balanced on the left side and the right side. And that is our final answer, earning us 3 marks over there and 20 marks for this whole section. Cool. So if organic reactions is getting a bit confusing at the moment, we're about to break down question 4 here of the June 2025 chemistry paper, where we're going to see the usual structure of a question like this, as well as revise some of the sections and get some useful tips to help us orient ourselves as we work through this question. Okay, let's jump right in. So question 4 says, the flow diagram below shows how an alkene, okay, can be used to prepare other organic compounds. The letters J to N represent various organic reactions. So this main guy here, it is an alkene. It looks something like this. So we have our meth, eth, prop, bute. So we have butene, and because this is on the first C over here, we can call it but1-ene, or we can just call it butene. A reminder that alkenes end in ene over here. So now that we can visualize what alkene we're dealing dealing with. Let's move to 4.1, where they are asking the first question having to do with the fact that this is an alkene. So 4.1 says, is an alkene a saturated or unsaturated hydrocarbon? Explain the answer. So 1 mark for the correct answer, and then 2 marks for the definition of whichever answer we pick, provided it is correct. So a nice way that I like to think about this, we have saturated versus unsaturated, and I sat down to sing is a little memory device that I use in order to remember that saturated are just single bonds compared to unsaturated, which also have double or triple bonds in the mix, which means our answer for an alkene has double bonds, which means we're dealing with an unsaturated molecule. So we just earned 1 mark for unsaturated, and then we just need to go ahead and write the definition for unsaturated, which is exactly what we were talking about now, where there are 1 or more multiple bonds, i.e. double or triple bonds, between 2 carbon atoms in the hydrocarbon chain. Great. So 1 mark for unsaturated, and then 2 marks for this over here, with 1 or more multiple bonds between 2 carbon atoms in the hydrocarbon chain. Okay, and they're always trying to squeeze some sort of definition into the first question of each of these sections, even if they don't phrase it as write the definition of unsaturated or saturated, for example. So this just earned us 3 marks. And then 4.2 over here says write down the type of reaction represented by. Okay, so we have a bunch of different letters going all over the place from this alkene, and we just need to see what has been added or removed or substituted in order to get the products on the other side of the arrows. Okay, a reminder that for this section we don't have to be specific with which type of reaction it is. By that I mean we can use the general terms addition, elimination, and substitution. We don't have to say hydration, dehydration, dehydrohalogenation. We can if we remember it, but we can always work with one of these big umbrella terms. It makes it a little bit easier for me because a nice way that I like to remember it is that addition goes from 2 things to 1 thing, okay? And elimination goes from 1 thing to 2 things. And then substitution is a 1 to 1 or a 2 to 2. By this, I mean in order for an addition to take place, we will need something like a double bond over here, because this double bond needs to break, and we need this plus something else, say a haloalkane or just a halogen or something like that, or a hydrogen, to break this bond and then form here, which means we would need this plus something in order to make 1 new thing. An addition means we have to look for any double or triple bonds, usually just looking at double bonds. Okay, elimination is just backwards of that, meaning we would have a single bond, and that single bond would exist, and we would remove something, and the only way this will still make sense is by adding a double bond back to it, which means we'd have 1 thing, we would remove something, and that something would live on this side, along with the thing that now has a double bond, meaning addition has a double bond over here where the 2 lives, and the elimination has a double bond over here where the 2 lives. And that's a nice way to remember that 2 is a double bond for addition and elimination. And then substitution, we can just deal with that by itself, considering that is just a 1 to 1. It means we are just swapping something for something else, meaning that we are going to remove, say now this H here, and just put a Cl in its place. But we haven't changed the main chain by any stretch. We haven't removed any double bonds or created any double bonds in doing that, which meant it goes from 1 to 1 or 2 to 2, and there aren't any bonds breaking on the main chain like addition and elimination. Okay, so with that, this makes it a bit easier for me to just keep this in mind as we approach these questions, because then I can see a lot easier what sort of patterns we're working with in order to deal with that. And then if we remember the specific names, then we can add them by all means. But this helps us and makes it a lot easier to study so that we can save time in our studies and focus on other sections as well. So with that, 4.2, write down the type of reaction represented by. 4.2.1, we have J over here. So a reminder that this is the but1-ene that we're dealing with, and then something happens. Sometimes they draw the thing on the line, sometimes they don't. But in this case, this plus something maybe goes to butane, which means that we went from but1-ene to butane. And in order for that to happen, and this double bond to break, for a single bond to live there, we would have to add something, because a double bond going to a single bond, remember that fits the brief of over here, 2 to 1, addition 2 to 1. So we have to add something. And in order for this double bond to break, and for this to still make sense, by that I mean there will now be a new H that can live here, and a new H that can live here, because this H and this H, these two guys, weren't required for the but-1-ene, but they are required now for the butane, considering this double bond went away and 2 new availabilities opened up on these 2 carbons, so that they both had 4 lines around each carbon, which means that we had to add an H2, because an H2 is missing in order to fill this gap over here and these empty spots. Okay, which means that that understanding helps us a lot, meaning that it is hydrogenation, should we want to write that down. But in a test, if we don't want to work all of that out, we can just see that there was a double bond and now there is no double bond, and that means it is just addition. So we can either write addition or hydrogenation, both will give us the mark, but if we see that it went from a double bond to a single bond, it means that it is addition, and we'll get our 1 mark for just writing addition over here. Okay, so we just earned 1 mark over there. And then 4.2.2, so the type of reaction represented by K over here. So K is from butane to compound Q. And there's not very much information, considering here we had information before, nothing on the line, and then something there. So we had 2 slots, and then there was a missing piece over here. Right now, we have something before, nothing on the line, and nothing afterwards. So that means there isn't enough information to figure out what happened at this stage or what happens at this stage. If they gave us something on this line, we could happily figure out what happens at compound Q, like butane plus something equals compound Q. But in this case, there isn't enough on this line, so we need to try and find another way to get to compound Q so we can understand what compound Q actually is. Because if let's go from here first, our alcohol to compound Q also isn't enough information to figure out what Q is. But from the middle here, we have this alkene over here, this but-1-ene plus HBr, and then we form the same thing that this butane plus something will form. Okay, that means we have to use this information plus this information to figure out what compound Q is, and then we can figure out what reaction had to take place to create compound Q from butane. Okay, so that means if we're looking at our alkene here and we're adding an HBr, it is quite similar to this previous reaction, considering we had a double bond, and in this previous case we added an H2. That was our hydrogen, our hydrogenation. But here we're adding an H and a Br, which will serve the same purpose as removing a double bond over there and creating this opening and this opening here for an H to join and a Br to join. Okay, which means we're ending with a product like this for our compound Q. Our compound Q then is 2-bromobutane, which means we can remove this because there's no longer a double bond over there, and we can just add our ane over here, which means compound Q is this guy, 2-bromobutane, because we have our Br on 2 and our double bond broke. Okay, which means now we actually know what compound Q is. And if we are looking at butane and how butane, a single bond, can go to another single bond, considering our double bond actually had to break based on our interpretation with this middle arrow over here, it means that a single bond to a single bond is just substitution, because here substitution is just 1-to-1, which means we can just write substitution over there. Cool, and that would earn us 1 mark over there, but for the sake of understanding, it means that we had a butane, something like this, with single bonds throughout, and then all we had to add was a bromine over here, a Br2 potentially, because bromine's a diatomic molecule. But with that, if we added a bromine over there, we would just swap out this H with a Br. And that is what's happening with a substitution like that, which means it was a straight chain with single bonds throughout. There were H's everywhere, and we just added a bromine to live here, and that would just swap out with the H, meaning that this is just halogenation if we want to know this specific reaction that is taking place. But either way, we earned 1 mark over there. And then 4.2.3, write down the type of reaction represented by M over here. Okay, so once again, with the same train of thought, we're trying to see we have the thing here, we do not have the thing here, and we do not have the thing on the line, which means we don't have enough information to work with this yet, which means we have to go to the second closest thing, which is this way over here, the bottom left, where our alkene reacts with HCl to form a major product and then a minor product. Okay, so what we need to do is first work with this portion here, which means we have, back to our drawing, we have prop 1ene, and then we're going to add an HCl, which looks very similar to our HBr. It is an acid, but we do not have to be concerned with the fact that it is an acid. We're treating it as if it is a hydrohalogen, which means just like this guy, we broke the double bond in order to attach the H and the Cl, which means that our double bond breaks, and then we add an H over here and our Cl over there, and the HCl joins this guy, forming the major product. And then one thing to keep in mind is the difference between a major product and a minor product, because right now there was no little byproduct that broke off. It's not like we have a plus H2O somewhere or something like that. If we were doing the reverse reaction for this, if we were to look this way with our arrow going like this, we would then remove our H, our Cl, that line, this line, form our double bond over there, and then our byproduct would be HCl, and this would be the minor product in most cases. That is what we refer to, especially in an elimination reaction. But in this case, they aren't referring to that. What they are referring to, though, in this specific example, is that now we have compound R, which fortunately for us, we're going to draw in 4.3, or we already have drawn it. So that's good. So we have the major product, but we do not have any HCl or H2O branching off as the minor product. But what they mean in this case for a minor product is the different probabilities of where the H and where the Cl will attach on our butane chain. Okay, because our H attaches here and our Cl attaches here, it's very common when a double bond breaks for our chlorine, our iodine, our oxygen, whatnot, to attach on the second C. It is because this is more stable. But with probabilities, sometimes the opposite can occur, meaning our Cl can join there and our H can join here, which means our Cl joins on the 1 over here, which means we have something like chlorobutane instead of 2-chlorobutane as it previously was. And a situation like this is called a minor product because it is far less common, because it is far more unstable when something like this occurs, meaning it is much more likely to break off and then form back into its usual product. Okay, so that means this is our minor product, and we've done all of that thinking just to see what our minor product is, to then go from this product back to our butene. Okay, which means we have to see that we have a single bond like this with a chlorine on 1, and that is the reason that our double bond is going to form on 1 over there again. And then what we're going to do is we're going to remove the chlorine, remove the H, and with that we're going to remove that line and this line, and then a double bond has to take place. And what this means is that we had a single thing, and then it is breaking off, forming a double bond, and then our byproduct is our HCl in this case, meaning the HCl that we removed there and there is now floating off in that beaker. Okay, which means we now have a double bond and a product, which means we went from 1 to 2, which means we're dealing with an elimination reaction. Okay, and the specific elimination reaction is dehydrohalogenation. We removed our H and our Cl. If it was hydrohalogenation, means we'd be adding it. But dehydrohalogenation, dehydrate, dehydrohalogenation means we are removing it, a hydrohalogen, from the compound. Okay, which means we can write dehydrohalogenation or we can just write elimination, and both will give us the marks. And in this case, just having written elimination earned us 1 mark over there. Okay, cool. And then 4.3 over here says write down the structural formula of compound R. So compound R, as we were talking about, is the major product that we were referring to in our previous explanation. Okay, so once again, we'll just do it quickly. We were dealing with our alkene over here, but then as we were talking about, the fact that we are adding an HCl means this double bond has to break, and we now have to add the H over here and the Cl over here on the second. Okay, and we don't add the Cl on the 1 because that is far less common. That is our minor product and less stable, which means if they aren't referring to major or minor products and there's a double bond over here on the first, always attach whatever joins our main chain, always attach that to the second carbon. Okay, that is just a good habit, and they don't always explain that, but that is what this means as far as stability, and that is why it is more likely to join our second than our first. Okay, cool. And then in the test, just draw all your other H's, and then we will get our marks. and we just earned 2 marks over there. And then 4.4 says for reaction N over here, write down 4.4.1, the type of addition reaction. Okay, so they want the specific type of addition reaction, meaning we cannot just use one of these guys. It is an addition, we just have to know what type of addition reaction it is. Okay, so we have an alkene, we have something plus something else goes to our alcohol over there. Okay, which means if we're back to our initial, like this guy, then in order for the alcohol to form, and we know it is addition, so it is 2 to 1 still, it means our double bond is going to break, and we're going to add something here and then something here, and our something here is going to be an H, and our thing over here, because of stability, always added onto our second C, will be the functional group of an alcohol, meaning it'll be our OH, our hydroxyl that makes it an alcohol. Okay, so right now we added an H, an O, and an H, meaning that these guys all joined here, which means that these weren't there before, which means that on our line over here that they didn't write, we have plus H2O, because that is what we're dealing with here. We're missing H2 and the O over there, and that will give us a full happy alcohol as our major product over here. And once again, they refer to major product, not minor product, meaning our OH is on the 2 over here. Okay, which means the type of addition reaction, we're dealing with hydration because we added water. Okay, and that just earned us 1 mark over there. So then 4.4.2 says 2 reaction conditions. Okay, so if something is hydration, it means that we need water present. Some other reactions require no water at all because the water will then interact with it. But for this thing specifically, hydration needs the water, so we need water, and that is 1 mark. Or writing excess water. Both variations will work for this answer. Okay, so we do need water, we need excess water for this hydration reaction to take place. And then the second requirement is some sort of catalyst. And when in doubt, we write sulfuric acid. We will learn the different forms, but if we don't have time to cover everything before a test, sulfuric acid or H2SO4 is a very common catalyst in a lot of reactions. Okay, which means we need a catalyst, we need enough energy for this to take place, and then this catalyst specifically is our sulfuric acid, our H2SO4. But when we look at our reaction sheet that our teachers have given us, sulfuric acid comes up quite a lot, and in a lot of the past papers I've seen H2SO4 as a good shotgun approach when we're talking about the catalyst that we're working with. Okay, but we'll learn each specific one as we work through different examples, but this is the catalyst that we're working with here, and when in doubt I would recommend just putting this down. Okay, and with that we just earned 2 marks over there for the 2 reaction conditions. And then 4.4.3 over here says the IUPAC name of the alcohol that forms, which means we have already drawn it here. We know that our OH is on the second C in our carbon chain, and they told us it is a major product, and that is also why it's on the second C and not the first C. Okay, which means our IUPAC name is meth-eth-probute. So we have butane, and then our functional group, our OH, our hydroxyl, is on 2 over here. So we have 1, 2, 3, 4, 1, 2, 3, 4. We always start our counting from the closest C to where our functional group is attached. Okay, which means we have 1 over here, 2 over here, 3 over here, and 4 over there, which means we're dealing with a 2. So we have butane, 2, and then ol. Butane because there are 4 C's in the chain, 2 because that is where our functional group is attached onto the second C, and then ol is the prefix that we have for an alcohol ending in ol like that. Okay, and then 4.5 over here says write down the IUPAC name of an isomer of butane. So it's 2 marks, and our butane is up here. Okay, so we have 3 different types of isomers. We have functional, we have positional, and then we have structural. Okay, the thing with butane specifically, if we have our butane over here, is that there is no functional isomer for butane because there are single bonds all around and we don't swap something. It's not like a ketone and an aldehyde or a carboxylic acid and an ester, when we can just remove something or add something and change the functional group but keep the same amount of C's and H's. With any alkanes, we cannot do that. So our functional is ruled out. Okay, positional is also ruled out because there's no double bond that we're moving. It's not like there's a double bond on 1 that we can then go ahead and move to 2, for example. So it means that positional is out because there are single bonds throughout. So there's no variation that we can do with the attachment for the functional group. Okay, which means our last arrangement is structural, which means for a structural isomer, we have to break the main chain and add a side chain over there, which means this is gone and we no longer have butane, but now we have our C branching off on the second C over here. A reason we can't add it on 1 or 3 is because it would still just be a long butane, just with a bent chain instead of a straight chain. Okay, which means we have to add our C over here in the middle, and then we're dealing with something different, because now our main chain is only 3 C's long, and we have a methyl attached on our 2. Okay, which means we are dealing with a structural isomer for butane, and when we do the IUPAC name, we always have to start with our side chain. Okay, so if we count either way, we're going to be on 2 over here, whether we counted 1, 2, 3 or 1, 2, 3. Okay, which means we're dealing with a 2 methyl, so we can have a little dash or hyphen in between there. So we have a 2 methyl, and then we have our long chain, meth, eth, propane. Okay, and there aren't any specific bonds to deal with, so we don't have a prop 1-ane or a prop 2-ane, because that only works for enes and ynes. So right now we just have our branched side chain where our methyl is attached on 2, so we have 2 methyl, and then we have our long chain, which is our propane. Okay, cool. And with that, we just earned another 2 marks. We can have a dash in between here, or we can remove the dash and put those two together like that. Both work, but either way, we wrote down the IUPAC name of an isomer, the structural isomer of butane, which is our 2-methyl propane, and that earned us 2 marks. Cool. And then last question, 4.6. And 4.6 over here says use structural formula to write down a balanced equation for reaction Al. Okay, and structural is in capital letters, so that's important. And this is for 5 marks. So structural formula for a balanced equation for the reaction of Al, where we have our alcohol joining up and forming our compound Q, which we saw was our haloalkane. Okay, so structural formula to write down the balanced equation. So let's write down the alcohol first, because we had drawn that previously, which I'll rearrange for us here, and then compound Q, and then we can see what we need in order to form it. Okay, a reminder for our alcohol, we had butan 2-ol, which means our O and our H was over here. We had an H over there, and H is throughout. Okay, which means this was on our left side of our reaction. This is one of our reactants, and we need to see, is there another reactant on the left or another product on the right, or what? But we'll get there. But we do know what compound Q looks like, because compound Q was our HBr when we broke our alkene and we added an H and a Br over there, which means it looks very similar. We just have something like this. Okay, and that means what we have here is a substitution, because this was here before and now this is here afterwards, which means our OH was swapped with the Br and the Br joined it after the arrow. Okay, which means we aren't dealing with an addition reaction or an elimination reaction, because there isn't 2 to 1 or 1 to 2. There are no double bonds breaking. But that means, as we mentioned, we're dealing with a substitution where we go from 1 to 1 or 2 to 2, which means we can't just go from 1 to 1 over here, because we don't have the other parts to replace them. We're missing some of the parts for all of this math to add up, which means we have to go from 2 to 2, which means what are we missing on this side? And the most common way is to not just add a Br and an OH, but to add an HBr. This is something that is on our reaction sheet, and this is the most common one when turning an alcohol into a haloalkane. Okay, so we add a HBr over here because the Br is missing, and we need this Br to join over here and this OH to join that H over there, which means once this Br has joined, what we have on this side as well, because a reminder that we're going from 2 to 2, is our H2O, because this OH joins that H when this Br joins over there. So the Br swaps with the OH and this OH joins this H over here, which means we have H2O, and that is what we have on the right side over here as our product, which means we have just completed this question, and we don't have to write HBr like this. We can, considering they ask for structural formula, but HBr like that is also okay, and we also don't have to write HOH, something like this, for H2O, because H2O is also okay like that. When they're referring to structural formula, they want us to just draw the structural formula of our organic compounds. Okay, and the structural formula specifically, not the condensed structural formula like CH3COH. We will lose marks if we draw them like that. Okay, so right now we have written everything. We've written the structural formula correctly where they wanted the structural formula, and we were referring to a reaction Al, and then we just need to see, is it balanced? And if something is going through substitution, we can by all means count all of the H's, all of the O's, all of the C's, all of the BR's. But if something is substitution, it is swapping identically. And that is why we add the HBR here instead of just a BR, because that would make it a bit trickier to add the BR and only swap one thing, because then we'd have an OH over here, and that is less likely to occur as a product by itself, because OH is something from acids and bases, and that is a hydroxide. Okay, which means adding an HBR and swapping it with the OH means that everything is balanced, and that we don't have to add any numbers anywhere. And usually when they're referring to a balanced equation in structural formula as well, we don't usually have to add numbers. So it just means we have to add the right reactants with it in order for it to remain balanced throughout. Okay, cool. And that just earned us 5 marks over there and 20 marks for the whole section. Cool. So if rate of reaction is getting a bit confusing at the moment, we're about to break down question 5 over here of the June 2025 chemistry paper, where we're going to look at the standard form for a question, as well as some tips to help us orient ourselves when we're in this section. Okay, so let's jump right in. So it says 3 different experiments are performed using the reaction between magnesium carbonate and hydrochloric acid. Okay, so we have our magnesium carbonate over here and hydrochloric acid over here. Okay, and we form our MgCl2, our H2O, and our CO2 over there. So we have 3 experiments in this question. Okay, so we're about to break them down one by one. So experiment 1 over here says in this experiment, magnesium carbonate, this guy over here, reacts with excess hydrochloric acid. So it means our MgCl is our limiting reagent, our LR over there, which means it runs out first, which means there's HCl left over. In a closed container at 23 degrees Celsius. Important. The reaction is monitored by measuring the volume of carbon dioxide gas produced over time. So we have our volume of CO2 gas measured. So this actually occurs, actually develops until it runs out, until our MgCO3 runs out, with our HCl being left over at the end. So we have monitored by measuring the volume of carbon dioxide gas produced over time. So we have our time in seconds. The molar gas volume at 23 degrees Celsius is 24 dm3. So our molar volume over here is our Vm. So that is 24, and they told us specifically what it is. So we don't have to reference our constant sheet, but now we do know our Vm over here. So that means we can go ahead and use this formula at some stage potentially. And then it says the data collected is shown in the table below. So we have our time, we have our volume, and as we can see, it goes up in 10 seconds at a time. And then our volume had a big jump in the beginning, and then a smaller jump, and a smaller jump, and a smaller jump. So it's kind of flattening off like that because our MgCO3 is running out. Cool. So that is all the information there for experiment 1. So 5.1 over here says define the term reaction rate. So this is a definition on our definition sheet, and it is reaction rate is the change in concentration of reactants or products per unit time. So this just earned us 2 marks over here. This is an all or nothing question, which means we either get it entirely right or not at all. And what we have is reaction rate is the change in concentration. So here we have our change in volume, but we can always mention either change in concentration, change in volume, change in moles, change in mass. Either of these options will work in prelims and finals. On this memo, it just says change in concentration, but we do need to speak about one specific variable that is changing from either our reactant side over here on our left or our product side. In this case, we're looking at our CO2. It is one of the products, and it is the change in volume, not concentration, but that's okay, of the reactant or the product in this case per unit time. And this also gives us our formula that we can use because we have a rate of reaction formula, which is the change in whatever variable we're looking at over time. And a reminder for this section that we're usually comparing a 1-to-1. We're usually trying to see how surface area affects rate of reaction, or the temperature, or the mass, or concentration, or moles over there. And we're comparing one of these things and seeing how it affects rate of reaction. In this case, we'll see experiment 2 over here has a higher temperature, which means they haven't changed the surface area or the mass or concentration or moles. They've just changed the temperature from experiment 1 to experiment 2. Prelims and finals focus on this setup a lot more. For now, they're just introducing us to the topic and keeping it quite linear, which is good, which means we have these big 3, and these have to do with our kinetic energy, because if we have a powder over a ribbon, for example, there would be more exposed particles, and and those more exposed particles would have more effective collisions. Changing, an increase in temperature, more EK, and therefore more effective collisions. Mass means we have a greater amount of product and therefore more effective collisions. And then the fourth thing over here is a catalyst. But this guy works a little bit differently because a catalyst just lowers our activation energy. It doesn't increase the kinetic energy or the amount of effective collisions. It just lowers the amount of effective collisions we actually need in order for the reaction to occur, which means we're looking at these big four, and in one of these questions, we're usually just comparing one of these things. As we can see here, we're looking at the temperature over here, and then in experiment 2, when we get there, we're looking at the temperature that has increased. This is the overview for this section, what we're trying to keep in mind as to what are we testing that affects the rate of reaction, and then this reaction rate definition just helps us with the formula to see that, okay, what we've been given on the table is in fact what we need to put in a formula at some stage, which is the change in this over the change in that. And with that, we're on 5.2 that says use the collision theory, very common question, to explain the effect on the reaction rate as time progresses. A reminder that when we were looking at the information just now, we saw that it had a big jump and there were smaller increments as it went on until it flattened off from 50 to 60 seconds over here, which means we ran out of our MgCO3 and there was just HCl left, which means these two guys could no longer react, no longer form sandwiches. If this was bread and this was polony, we ran out of bread, so we just had polony and we couldn't make these sandwiches over here, is an analogy I use with some of my students, which means we have to use collision theory to explain why the reaction rate decreases as time progresses. Because here it's super steep, and then here it's slightly less steep, and then it gets less steep and less steep and less steep until it flattens off over there, which means we have to look at the number of particles. So this is 4 marks, 4 bullet points. We're going to say the number of particles per unit volume decreases, which means these guys are colliding, this bread, this polony in this one beaker, they are colliding, which means the number of particles that we actually have because we are forming these products is becoming less per unit volume, per little increment that we are measuring this beaker space in. And then linking here to our EK, we have fewer particles with enough energy available for collision, which means as they're colliding, we now are losing energy, and therefore there are fewer particles that are actually converting from the reactants to the products. And then point 3, this has to do with the effective collisions that we were talking about here, which means there are fewer effective collisions per unit time. Okay, and a nice way I like to think about that is that there are these different MgCO3s and different HCl's, and I'm imagining like a lock and a key basically. So this guy is like this and this guy is like this, and as they bounce around, this is kind of like an enzyme and a substrate in life sciences, is when they bounce around, they have to bounce around and hit with the perfect orientation in order for them to break up and convert these new things. So if there are fewer effective collisions per unit time, it's because we have fewer particles that end up colliding into each other like a perfect lock and key to unlock each other and break up. So that is what fewer effective collisions per unit time means, and that's just how I like to think about it, because there are fewer of them bouncing around with the perfect orientation to actually break up from this reactant, from the MgCO3 and the HCl, to form these products over here and form these new things. And therefore our final point over here is reaction rate decreases, and that is our 4th mark, which means we're looking at temperature. We're seeing that number of particles per unit volume decreases because the reaction is slowing down. We have fewer particles bouncing around inside this cylinder or beaker or what have you, and therefore fewer particles with enough energy available for collision to actually convert, and then fewer effective collisions, fewer perfect lock and key collisions in order to convert our reactants to our products. And with that, our reaction rate actually decreases until it tapers off and it no longer produces any more volume of CO2. And with that, that is collision theory, and that explained the effect on the rate of reaction as time progressed, the fact that reaction rate decreased, and that earned us 4 marks. And then 5.3 over here says calculate the reaction rate for the production of CO2 gas during the first 20 seconds in dm3.s to the -1 for 3 marks. Okay, so the reaction rate for the production of CO2 during the first 20 seconds, okay, from 0 to 20 in dm3.s to the -1, which means they have given us the units for the formula that we need to use for our rate of reaction, because our rate of reaction is the change in whatever we have, in this case volume, of either the reactant or in this case the product per unit time. So if we were to put that in a formula, they can always give us different units, and they do give us different units based on whatever we're measuring, which means reaction rate is just whatever whatever we were measuring over time, which means reaction rate is this, and we want dm3. What we can see here is that we're in cm3, so we're in the wrong unit, but that is a relatively straightforward fix that we're about to do together, which means we just have to do a conversion dot s to the -1, which means we have our dm3 over our s to the -1, or s to the +1, and when they take it to the top, that's why it becomes times s to the -1, and that is how we work with the units in order to create the formula that we're working with, which means we have our dm3 over our seconds, and we're taking it during the first 20 seconds, so from 20 to 0. So we have to do the change in dm3 over the change in time, which means over here we're going to just do our conversions first and then plug them in. So 20 over here, we're taking the final minus the initial. In this case, we take the 300, but in order to convert from centimeters cubed to decimeters cubed, we have to divide by 10 cubed, okay, which means divide by 1,000. So centimeters to decimeters is divided by 10, but because they are cubed units, we put a cube over there, which means we end up dividing them by 1,000, which means we have 300 divided by 1,000. So we can put that over here. 300 divided by 1,000 is 0,3, which means we have 0,3 over there, minus the 0 is 0 in this case. And then our change in time is 20 minus 0 as well. At this stage, we've converted centimeters cubed to decimeters cubed. We've done the change. We always take the minus of whatever our starting point is, because it isn't always necessarily 0. Sometimes it would say from 40 seconds to 20 seconds, and then we'd have to go 40 minus 20 and plug that in over here after having done the conversion. Same thing with time. We have our time already in seconds, so that's good. No conversions for us. And then the change is from the same endpoint to the same starting point, where we have 20 minus 0, which means at this stage we can just plug this in our calculator and we will have our answer, which means we have 0,015 dm3.s to the -1, considering they gave us the units that they wanted in. And that just earned us 3 marks over there. And we don't get a mark for the actual formula. This formula just helps us orient ourselves as to how we are approaching this section. So you can put change in volume, you can put change in dm3. They don't actually allocate a mark for the formula, but these units help us see what we need to put at the top and what we need to put at the bottom, so we can then work out our answer. And then question 5.4 over here says calculate the mass of MgCO3 required for this experiment. So this is stoichiometry now, and it has to do with limiting reagents over there. So we need the mass of the MgCO3 required for this experiment. So it's always nice to rewrite this whole formula down, so I'm just going to go ahead and do that. The reason I write this down is so that I can see the molar ratio of the numbers in front, and also so I can see where I'm starting in this whole equation and where I'm ending up. Because if we are calculating the mass of MgCO3, it means that this mass is unknown. This MgCO3, this limiting reagent, is unknown. And if this guy is an excess, it means we don't work with that or start with that. And our MgCl2 and our H2O, we don't have any information on it. But our CO2, we do have info on, which means we're starting at our CO2, trying to get something in moles, then do a molar ratio, and then calculate the mass over here for our MgCO3. It just helps me see where we're starting and where we're going, and what information we have to start with, and what information we need in order to calculate what they're asking for. Which means if we actually have the amount of CO2 that was measured, it means it is based on the limiting reagent, not the thing in excess. In the beginning, they gave us the VM over here at this specific temperature at 23 degrees Celsius, which means we're going to work with where this experiment ends, because this 500 here that hasn't increased from 50 to 60 seconds is the stage where our MgCO3 ran out, which means we're going to work with our V of 500. But a reminder that this is cm3, so we need to convert it. We need to divide it by 1,000, which means our volume is 0,5 dm3. So we're looking here, we just did the conversion so that we can then work with decimeters cubed like our VM here. But if we have V and we have been given VM, which is 24 dm3, then we can go ahead and get our moles for our CO2 here and then do our molar ratio over here, which means N equals V over VM on our formula sheet is the easiest way with this information to get into moles. And then our moles is 0.5 over 24, and in our calculator this will give us an answer of 0.02 mole. So right now we have the mole, and we can see that we're working with CO2, which has a value of 1 over here for its moles, and we're jumping in there to MgCO3 with a molar ratio of 1 to 1, which means in our moles for our CO2 is 0,02, and that means our MgCO3 over here, its moles is also 0,02, and that's great for us because we started here, we've done our molar ratio, and now we can work in our mgCO3 where we're calculating the mass, which is also good for us because we can always calculate the molar mass on our periodic table. Okay, so if we go ahead and write our formula so long, we have N equals M, what we want, over capital M. That's the molar mass. MR also means molar mass, but we work with capital M over here. And then we have the amount of moles, we have the 0,02, and then we want the mass of the mgCO3 required to have created this 500 centimeters cubed of CO2. And then it is over the molar mass of Mg is up here. Mg has a molar mass of 24 plus C has a molar mass of 12 over here plus O, which is 16 over there, times by 3. And then we can just go ahead and solve for this in our calculator because we need to isolate for our mass by itself, which means we can simplify all of this at the bottom, take it up to the top and multiply it there. And then we have M by itself, which means over here at the bottom we have 84 grams per mole, and we have our 0,02 there still, and then 0,02 multiplied by 84, and that answer is 1,75 grams is our mass over there, which means we now have the mass of mgCO3 required for this experiment. We needed 1,75 grams of it in order to produce 500 centimeters cubed of our CO2 over there. And that is our final answer, earning us 4 marks for that question. Okay, cool. And then we're on experiment 2 over here, and question 5.5 says experiment 1 is repeated. So the same experiment over here is repeated, but this time at 30 degrees Celsius instead of 23 degrees Celsius. So at a higher temp. So it says the following Maxwell-Boltzmann distribution curve was produced. So this was experiment A and this was experiment B. So we have 2 different experiments and we need to see which one aligns with experiment 1 and which one aligns with experiment 2 based on our understanding of the Maxwell-Boltzmann distribution curve. So on our left over here, it says number of molecules. So this is how much of the substance we have before it converts and becomes a product after our activation energy. And then at the bottom over here, we have our kinetic energy, which is the amount of energy each particle has. So we're just looking at the number of molecules or particles and the kinetic energy they all have. So 5.5.1 says which graph A or B best represents experiment 2, where we have the higher temperature. The previous temperature was 23 degrees Celsius, and now we're dealing with 30 degrees Celsius for experiment 2, which means our answer for this question is graph B, and I'll explain why. So graph B over here has a higher kinetic energy at its peak, which means it has increased in temperature, and therefore once we get here to our activation energy, we end up having more reactants that are converting into products. If we're looking at something like an exothermic or an endothermic, what we have is our activation energy required, the amount of energy required in order to convert from reactants to products. This is our activated complex, but our activation energy is how much we need from our reactants to the peak in order to start converting into products, which means our EA is lining up here. And if we have a higher temperature, just like over here, we have a greater EK, and therefore this is aligning with our activation energy for our endothermic or exothermic graphs, and we have more molecules that are over the activation energy having effective collisions and therefore converting from reactants to products, which means that graph B represents experiment 2 because of the higher temperature. That is one way of looking at it. Another way I like to think about this specific section is when something has a lower temperature, so experiment 1 with the lower temperature, there are more molecules that are too cold and therefore stacked nearer our y-axis. So they're cold, they're shivering, they're over here all close to this y-axis, and therefore they cannot convert. So we have a more stacked higher peak closer to our y-axis where the number of molecules all have a very low kinetic energy. Therefore they're over here, they're peaking early by the y-axis and therefore do not have enough energy to convert. But the conversion isn't taking place here. That isn't where we're measuring it. It's where we measure here where our activation energy is in terms of kinetic energy, which means as we come down here, there's fewer number of molecules that are greater than the activation energy and become our products over here. So 2 ways of looking at it. We can either see that an increase in temperature increases our kinetic energy and therefore our peak is further along, or we can think that because this guy is cold, all of these guys are shivering nearer the number of molecules and they all have a lower amount of kinetic energy because there is a lower temperature. So 2 different ways of just distinguishing between A A and B and which one has the higher and lower temperature, and also mapping that onto our activation energy for a graph like this guy, where we're looking at an endothermic or an exothermic reaction. So let me know if there are any questions in the comments below on that, and we'll check out other examples in further videos. But for now, we just earned 1 mark over there for saying graph B. And then 5.5.2 says explain the answer to question 5.5.1, and that is what we were just mentioning now. And we have to give 2 points where we can say a peak at a higher kinetic energy, which means our peak over here is higher in terms of kinetic energy than this guy over there, i.e. shifted to the right. And then therefore the second part of it is talking about the more molecules that have a greater EK than our activation energy. So we write more molecules EK, their kinetic energy is greater than the activation energy over here, which means we get a little bit more conversion from reactant to product. And that just earned us 2 marks over there, talking about the peak and then the amount of molecules that actually convert from our reactants to our products. And then question 5.5.3 says if a catalyst was added, would the line representing the activation energy, EA, be drawn to the left or the right of the current line? So are we drawing something here or are we doing something here? If we have a catalyst, will we have fewer or more products being formed from our reactants? So in terms of kinetic energy, it isn't changing how much the peak occurs. That has to do with temperature in this example, but it does shift our line to the left over here because it lowers the activation energy, which means that more particles, based on our last answer, will have enough kinetic energy, a greater kinetic energy than the activation energy, which means all we have to write over here is left. Because if we look down here, a catalyst, as we'll see in this example, lowers our activation energy, which means we need less energy in order to convert reactants to products. And that is exactly what's happening here. We're shifting it to the left so that we end up having more products with a greater EK than the EA. And therefore we get more products out because they require less energy to convert. So that just earned us 1 mark. And then experiment 3, 5.6 says experiment 1 is repeated again, but a catalyst is added and the following graph is obtained. So now we're dealing with an exothermic reaction like this guy. So exothermic lets heat out, endothermic takes heat in, but the catalyst was added and the following graph is obtained. But as we can see, this dotted line is our catalyst lowering our activation energy. Okay, and then we have our heading, a catalyzed chemical reaction. We have our potential energy on the left and the progress of the reaction on the x-axis over here. So then 5.6.1 says, is the reaction exothermic or endothermic? So as we were just mentioning now, it is exothermic because our products have less energy than our reactants, which means we're losing heat from here to here, and exothermic means losing heat. So 1 mark for just writing exothermic, and always write it exactly how they want it over there. You won't get marked down if you don't put it in capital letters, but it's just a good habit to write whatever they're asking for in the way that they've given it. Okay, so 1 mark for knowing that this is an exothermic shape. And then 5.6.2 says which letter represents the activated complex. So they haven't specified whether they are looking for the activated complex of the catalyzed reaction or the normal reaction, which means our activated complex, our complex is the peak over here or over here, which means we can either write B or D because these are 2 different pathways for the same reaction, one without a catalyst and one with a catalyst, but the activated complex is still the peak and they've given us letter options for either or, which means just write one answer down, either write B or write D, and we will get our mark. But don't write both, so just pick one and you will get your answer. And then last question of this section, 5.6.3 says give the value of the activation energy for the forward catalyzed reaction for 1 mark. So forward catalyzed is the dotted line over here, reaction, which means our activation energy is from our reactants all the way up to the peak. In this case, we're looking at the catalyzed reaction and they've given us the amount of kilojoules over here. This is the line from our reactants all the way up to the peak of the catalyzed reaction for the forward reaction. It means we can just write 10 kilojoules and that'll be our final answer over there. So we just got 1 mark over there and 20 marks for this whole section. So if chemical equilibrium is getting a bit confusing at the moment, we're about to break down question 6 over here of the June 2025 chemistry paper. So let's jump right in. So it says the reaction between carbon disulfide over here and chlorine gas over here, okay, this is already balanced, reaches chemical equilibrium going both ways in a closed container at constant temperature. The products that form are carbon tetrachloride, okay, so we have this guy, and sulfur dichloride, this guy over here. The balanced equation for this reaction is given and below, balanced, happy days. And then we have our delta H is less than 0, which means that we are dealing with an exothermic reaction. If this is negative, then it means we have something like this, where our reactants are here, our products are here, and if we do our delta H, which is our E of our products minus our E of our reactants, let's call this guy 2 over here, and our reactants, let's call it 10 over there. This is for our potential energy, which means we have 2, which is the E for our products, minus 10 over there, which is the E for our reactants, which means we have negative 8 kJ. So this is kilojoules. This is just an example to illustrate why delta H being less than 0 is negative, and therefore an exothermic reaction. So we've broken this portion down. We have our reactants. We know it can go both ways. We have our products, and then we know that it is exothermic, meaning it releases heat. And then at this stage, it says initially an unknown quantity of CS2 gas and 5 moles of Cl2 are placed in a 2DM3 container and allowed to reach equilibrium, which means we can go ahead and rewrite this, which I find quite helpful because then we can attach what information they've given by the reactant or product that it is relating to, which means initially an unknown quantity of this guy. So we have an unknown quantity, the unknown mass, and 5 moles of this guy. So we have an N that is 5. The moles will also be unknown over here, are placed in a 2DM3 container. So we have our volume, and that's already in decimeters cubed. This is very important stuff for the rice table specifically. Okay, and allowed to reach equilibrium. The equilibrium mixture contains 0.8 moles of CCl4. So at equilibrium, so that portion we'll deal with our rice table, but let's just write N of E over there is 0.8. And the equilibrium constant, our Kc up here, for the reaction is 0.36. Okay, we'll deal with that when we have our products over our reactants when we work with Kc. And this is the concentration portion, which means we have the information here. We can then start to work with it in the right formats as we approach each question. So 6.1 says, state Le Chatelier's principle for 2 marks. Okay, so this is just something we have to know on our definition sheet. And it says, when the equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that will oppose the disturbance. So we just earned 2 marks here. We'll break this down now, but it is not an all or nothing question. We can get 2 marks if we have all of these portions, and then we'll lose a mark if we don't have one of the following underlined. So equilibrium in a closed system is disturbed is 1. Reinstate a new equilibrium is another. And then favoring the reaction that will oppose the disturbance. So it's almost everything, but the key phrases are equilibrium in a closed system is disturbed, reinstate a new equilibrium, and then favoring the reaction that will oppose the disturbance. Which means if we left out this last portion, we would get 1 out of 2. If we left out 2 different underlined phrases, we would then get 0. But what this means is an equilibrium in a closed system. So these guys are in the same beaker over here. We've started with our reactants, and then it goes one way, and then the reaction stops. And then it will reinstate a new equilibrium. So it reaches a new equilibrium, and it stops going both ways. But then if we do something to either side, say now we add more Cl2 into this whole beaker, it will favor the forward reaction. So it's a constantly flowing equilibrium based on whatever disturbance we add to the system. So if we add more on this side or do something else, as we'll break down in the later Le Chatelier questions over here, it will then counteract that disturbance moving the other way. So if we add something more on this side, it will favor the forward reaction. If we add, for example, more CCl4, then it will favor the reverse reaction. But if there's too much on one side, it moves the other way. A nice analogy is a seesaw. If we have too much, it goes up and it slides down. Or if we have too much, it goes up and it slides down. And the system is constantly trying to balance itself in terms of the amount of mass of each product, in terms of any temperature changes, and in terms of any volume or pressure changes. Okay, but at this stage, the equilibrium in a closed system in a beaker will reinstate a new equilibrium, will find some new balance favoring the reaction that will oppose the disturbance, meaning that if we have more here, it will favor the reverse reaction so that they end up being balanced in the end. Okay, so this is what these words mean, and these are the important phrases to earn us 2 marks. Okay. And then straight from there into 6.2, an 8-mark question for a rice table. So 6.2 says, calculate the initial number of moles of CS2. So the CS2 over here, when I initially wrote it was mass, but potentially moles, we are dealing with the initial moles that we want. So required for 8 marks. So we will go ahead and draw our rice table. So we've just drawn the rice table. We're about to break it all down. We have every single reactant and every single product because they're all gases. If they weren't gases, then we wouldn't put them in here. Any solids do not come in here, but they're all gases, which means we account for both of these reactants and both of these products. And then rice with the C equals N over V at the end. Rices is what some of my students say, and I imagine some of your teachers taught you that. So we have our ratio. That means it's our initial ratio in terms of moles of the numbers in front of each of these guys, which means we have our R over here, which is 1 for our CS2 because there's no number in front of here. Cl2 has a 3 in front of it, which means we put a 3 over there. CCl4 has a 1 in front of it, so that's our ratio. Same with S2Cl2. So we have our initial molar ratio. A reminder that all of these guys for rice have to do with moles, which means initial is what we want for our CS2, which means we do not have that. Okay, so our initial, we can put a question mark or an X, depending on whatever is easier to work with. Sometimes we have to use an algebraic equation in order to figure out, especially when it comes to the change. But for now, I think a question mark might work for this guy. So then we have our initial moles of Cl2. They said initially an unknown quantity of CS2, as we said, question mark here, and 5 moles of Cl2. So we have an initial of 5. And then the equilibrium mixture contains 0.8 moles of CCl4. So the equilibrium, our E, our I is our initial, our C is our change. This is where we do a ratio here. We'll break this down. And then our equilibrium is also in moles. So we have our ratio, our initial moles, our change in moles, our equilibrium for moles and where it's ending up. And then from there, we can use our equilibrium to calculate our concentration, C equals N over V. And then as they mentioned, the equilibrium mixture contains 0.8 moles of CCl4. So we have equilibrium over here, we have 0.8. And then one thing to keep in mind is that there was no initial amount of mole for our CCl4 and our S2Cl2 because we put our CS2 and our 3Cl2 into a beaker and then the forward reaction takes place first always. Sometimes there would be an initial amount, but in this case there was nothing, which means we can just put 0 over here and 0 over there, which means at this stage what we're looking for is our change, and the only thing that we have an initial and an equilibrium for is our CCl4, which means we see that we changed by a positive 0.8 from nothing being here to us having 0.8 moles over here. And this change is the most important because everything changes in a similar ratio, which means that if this guy had a 1 and there was no mole and then it changed by 0.8, it means that this guy also has a 1 for its ratio, which means it also changed by 0.8 over there because the molar ratio is equal to the change, which means it is the same for the 1 over here, except we aren't gaining 0.8, we're losing 0.8 because right now we have negative 0.8 because the molar ratio says a 1 to 1 to 1. We've ignored 3 for now, which means we have plus 0.8, we have plus 0.8, and we have minus 0.8. And then the only guy that's a bit different is this guy because it has a 3 as its ratio, which means we have to go 0.8 multiplied by 3, which is 2.4. And this guy is also a negative. So what we can see here is that we had to multiply this by 3, and that gave us the amount of change of the moles based on the fact that there was a ratio and that this guy was 3 times bigger than that guy, which means we have a negative here, which means we now have the change in the amount of moles for all of these guys, which is very important. And then we can go ahead and calculate the equilibrium. And then from there, we can see what we're working with. Right now, I don't think we have enough information to just isolate for one of these in order to calculate the initial number of moles, which means we're going to have to go ahead and plug all of that in to our Kc in terms of X, because this X is unknown, which means if we are just calculating our equilibrium here, we also have a 0.8 as the equilibrium amount for the moles for our S2Cl2. At this stage, our Cl2 is 5 minus 2.4, which means we left with an equilibrium of 2.6 over there. And then here for our equilibrium, we have X minus 0.8 because we don't actually know what the the equilibrium amount is yet. So then from there, we're going to have to go ahead and plug all of these into our concentration formula. The reason we want our concentration is because our Kc is square brackets, and square brackets means the concentration. So we've done our rice portion all in terms of moles, and now we're trying to get the concentration so we can then go ahead and plug it in our Kc, which means our mole amount that we take at equilibrium for this guy is x minus 0.8, and then our volume, which was very important as they mentioned here, was 2 decimeters cubed. So it's already in decimeters, which means we don't have to do a conversion, so we can just go x minus 0.8 over 2. And then same thing here, but these guys aren't going to be algebraic equations, which means we have 2,6 divided by 2, which equals 1,3. Simplify them as far as you can so that we can plug in our simplified versions into our Kc formula. And then over here we have 0,8 divided by 2. All of these guys following the same formula as this, which means it's 0,4 there, and this guy as well will be 0,4 because it is the same amount. Okay, so at this stage we've earned about 3 marks, which means most of our marks are earned in our Kc formula. So let's go ahead and write down our Kc formula over here, where we have Kc equals the concentration of our products over the concentration of our reactants. And a reminder that these are all gases, that's why we could put them in there. And before we plug in our values, we do get a mark for writing down the format correctly, which means we have Kc at the top, we have our concentration of our 2 products not in the same brackets. So we go concentration of CCl4, we've put that there. And then for this section, we will put the exponent of whatever the ratio number is. By that, I mean we're putting it to the power of 1 because our ratio number is a 1. So all of these guys will be to the power of 1, except this guy will be to the power of 3. So that's just something to keep in mind. And then our other product is our S2Cl2, and that is also to the power of 1. And then for the concentration of our reactants, we have the concentration of CS2 over there to the power of 1, and we have our Cl2 to the power of 3 based on the ratio number. So now that we have the setup, the format over here, we've just earned 4 marks, and we can start to plug in the values that we've calculated and that have been given to us, because they gave us the Kc for this reaction at 0,36 over there. So we can plug that in, and then we have calculated the concentration of these guys. So our concentration of our CCl4 is 0.4 over here. We can now just sub them in normally. These square brackets just told us that it has to do with concentration. And then we also have 0.4 over here for our S2Cl2. And then for the CS2 over here, this guy, we have our concentration as x minus 0.8 over 2. So we can either rewrite CS2 and then isolate this later, or we can substitute this in so long. So that means we have x minus 0.8 over 2. That is the concentration in terms of x for our CS2. And then our Cl2 is 1,3 to the power of 3. We're just going to go ahead and solve for x. So at this stage, what we want to do is get x by itself. So the easiest way that I can see for us to do that is to take our x minus 0.8 over 2 to the top over here and bring our 0.36 down here. So we're just going to cross multiply to get our x on one side by itself, along with everything else that was in the bracket, because we cannot just move the x separately. So we have this over here. We've moved this guy to the top left, including the denominator, but we're just keeping the denominator in line. And then our 0.36, we're bringing down to its position. So we have something like this, which makes it a lot easier for us to work with, because now we have numbers by itself over here. And then we can just go ahead and move our 2 to the top as well, cross multiply it up. So we can times it by 2 over there. That guy's gone. And then it is minus 0.8, which means we can just go ahead and plus 0.8 over there, which means we have removed everything, cross multiplied that, done the inverse sign, minus 0.8, making it positive 0.8, and now we have x by itself. If you don't prefer this method, then just isolate each term and solve it part by part. But right now, this is just showing us ultimately where we're going to end up. We have x by itself, and then this whole right side, we can just plug in our calculator and get our answer for x. Okay, x equals 1,20 mole. And that is our final answer there, because we solved for x. They want the initial number of moles, and x by itself is the initial number of moles. The minus 0.8 over here already accounted for the fact that we weren't working out the equilibrium. Once we took it over, we got x, and x represents our initial moles for CS2. So 6.2 is done. We just earned 8 marks over there, and then 6.3 over here is now moving on to Le Chatelier interpretation questions. So it says, how will each of the following changes affect the yield of our S2Cl2 gas over here at equilibrium? So write increase, decrease, or remain the same. Write it exactly as they've given it in capital letters and with the same wording, just to make sure that you get your marks, and give a reason in terms of the reaction which is favored, whether the forward reaction or reverse reaction is favored based on whatever they're doing here, and whether we're getting less S2Cl2 or more S2Cl2. If the forward reaction is favored, we will get more S2Cl2. If the reverse reaction is favored, we will get less S2Cl2. So then 6.3.1 says carbon tetrachloride. So our carbon tetrachloride, our CCl4 over there, is removed from the system. So this is quite a nice one. What this is talking about is that if this guy is decreased, I always like to think about the increase first, because that makes it a lot easier for me to orient myself so I know what's happening in the system. So if CCl4 increased, for example, it would then increase more on this right side, and our seesaw would go up, which means it would fall down the hill to this side, and then these guys would balance, favoring the reverse reaction. But that's not what they said. I just started that way because that helps me orient myself. But what they did say is that the carbon tetrachloride is removed from the system, i.e. it was decreased until it was gone, which means that if we were to decrease this, our seesaw is going up like that, which means it's going to fall down the slope and it's going to favor the forward reaction, which means that if our forward reaction is favored, considering this has been decreased or removed, therefore our S2Cl2 is going to increase. And the wording is removing CCl4 will decrease the concentration of our products, and therefore the system will favor the forward reaction by increasing the products. Therefore, concentration of reactants will decrease and the concentration of our products will increase. This has decreased, therefore it will favor the forward reaction. The concentration of our reactants will decrease and the concentration of our products, our S2Cl2 that's remaining, will increase. And that just earned us 2 marks over there. Okay, when we look at adding more mass or decreasing mass or changing concentration on either side, we think the seesaw analogy. But then 6.3.2 says the volume of the container is increased. When we're looking at volume, we are looking at moles, and we are looking in terms of the cave analogy that we're about to break down, which means over here, the volume of the container is increased. So right now we also have our equation over here. So I'm just going to work around this guy, which means we had a beaker of a certain size, and then they increased the size of that beaker. So we now have a bigger beaker that we're working with. If the volume increases, so this is an analogy I've used in one of the other lessons. If our volume increases, so now we have 3 dots in here, and now we have those same 3 dots in here, but we have increased the volume. It means that the actual space that these same amount of particles are living in has increased. So our volume has increased over here, the actual amount of space, which means the pressure then decreases because these guys can bounce around into each other and hit each other more. But based on how much more room there is here for these guys to bounce into each other, they are less likely to bounce into each other. So they have more room to work around and therefore less pressure. And that's the important thing, because volume just helps us look at pressure. And then pressure means we have to look at the amount of moles on either side. In this case, there are gases on all sides, which means we don't have to ignore any solids in this reaction because there aren't any, which means we have to add up the amount of moles on each side. And then with that, we can interpret the relationship between the moles and the pressure, which means right now we have 1 and 3, which means we have 4 moles total on our left side over here. And on the right side over here, we have 1 and 1, which means we have 2 moles over there on the right side. So now that we have this setup having to do with how volume affects pressure and with the fact that we're looking at the amount of moles, we're then trying to link it now. So just like the previous question, I like to go up first with something to see how it affects it, so I can then work backwards. By that, I mean when we increased the amount of mass on the side, it went the other way. So what we're going to look at is that based on the amount of moles, if we were to increase the pressure, it would then move forward in this case. Because too much pressure, imagine we're like in a cave, okay? And there's 4 people in a cave, and there's too much pressure. The cave is too tight, there's closing in. That means these guys are going to want to move away where there's more space and fewer people, and balance out like that. That's how I like to think about pressure. How I like to think about the mass is the seesaw. How I like to think about volume relating to pressure is a cave analogy, where that if pressure goes up, there's too little space here for these guys in this cave, and therefore they're going to move to the place where there's more space. It will go from high to low. But once again, we're saying that so that we can see that, okay, our volume has increased, our pressure has actually decreased, which means it is going to favor low to high. And it is moving from the side with the lower amount of moles to the side with more moles, which means, based on the fact that we're looking at how this affects the yield of S2Cl2, our S2Cl2 is going to decrease in this beaker, which means we can just go ahead and write decrease. So quite a few analogies there, but now we're just going to put those into words based on everything we've just spoken about. So it has decreased our S2Cl2 because volume has increased and therefore pressure has decreased. In an exam, just write out fully. I'm just writing shorthand for us just so that we can see the link. The system will counteract the change by favoring the reaction that produces the greater amount of moles. As we mentioned, it goes from low to high. It favors the direction where there's more. And last point, therefore the reverse reaction is favored, i.e. the concentration of these guys will go down, our products and our reactants, their concentration will increase. So that just earned us 2 marks over there, and that is how we look at volume and how that affects pressure and how that relates to moles. So 6.3.1 has to do with seesaw analogy, 6.3.2 has to do with the cave analogy. And then there's no 6.3.3, but I am going to add one because we've looked at almost all of the signposts that relate to Le Chatelier. How mass affects something with the seesaw analogy, how volume relates to pressure, which affects moles based on the cave analogy. And then the only other signpost that is a bit different is the exothermic or endothermic and where heat is released. So we're just going to break that down just so that we can group all 3 of these together so that we understand all 3 of the signposts. I do this with all of my students, and it's quite helpful to just group them together like this, which means this guy, as we were talking about initially, is an exothermic reaction because it has a negative delta H, a negative enthalpy, which means that this reaction is releasing heat. But this formatting doesn't help us orient ourselves super well with this section. This actually confuses us quite a bit. This is just helpful just so that we know that delta H means exothermic releases heat. And if something releases heat, it means we have heat on our product side. So these guys are reacting, they are releasing or creating these products, and they are releasing heat. So if something was endothermic, it means it would take in heat and we'd have heat on our reactant side. So we just want to treat it like this, ignoring this guy, except for the interpretation of whether it's exothermic or endothermic, so that we can then treat heat just like we would a product. By that, we can look at the seesaw analogy again, because in this case, let's say increased heat in system. Okay. So if they increased the heat in this system, in this whole beaker where all of these guys live, and we know this is an exothermic reaction and heat has been released, it means that heat has increased in the system, which we treat just like we would if we were adding more of a product, which means we're adding more heat. It means our seesaw gets unbalanced, okay? And therefore it falls down the slope to rebalance again, which means our reverse reaction is favored in this case. So this just helps us treat heat just like we would a product by knowing that exothermic releases heat on the right side, endothermic has the heat on the left side with the reactants. And in this example specifically, we're not going to write down all the words, we're just seeing how this would affect the yield of S2Cl2. If heat increased, it favored the reverse reaction, therefore we would have a decrease in our S2Cl2. Okay, which means we can treat heat just like we would a reactant or a product in terms of mass with the seesaw analogy. Okay, so that is just a nice way to group those signposts. These are the most common ones. Sometimes we look at KC, but we'll get to that in other videos. But for now, these are the big 3 and they ask them all the time. Okay, cool. And then 6.4 over here says the graph below shows the changes in the rate of the reaction after further changes were made to the equilibrium mixture above. So we have our rate in mol.s to the -1 1 on the y-axis, our time in minutes on our x-axis, and our forward reaction is our solid line, and our reverse reaction is our dotted line. So we will interpret all of these, but when they are straight, that means equilibrium has been reached, and then at the 5-minute mark, for example, and the 15-minute mark, certain changes were made in order for this system to either move forward or backwards based on whatever disturbance we've added to the system. And then 6.4.1 says the equilibrium was disturbed at 5 minutes, as we just mentioned, due to a change in the concentration of CS2. Was this concentration increased or decreased? So what we're looking at is they did make a change to the concentration of CS2 at the 5-minute mark, and that caused a sharp drop in our forward reaction, which means that if we have a sudden drop in our forward reaction, it means we have decreased the amount of CS2, which means we were going this way, but then we dropped it suddenly, which means we have decreased the concentration of our CS2 because the equilibrium was disturbed at 5 minutes due to a change in the concentration of the CS2, which means was this concentration increased or decreased? As we can see, our forward reaction rate drops very suddenly, which means it was decreased. So we can just go ahead and write decreased. And considering they decreased the concentration of CS2, it means our reverse reaction was favored. And once we reach equilibrium, considering we have less amount of concentration, less amount of particles in this whole container, we have fewer effective collisions, and the overall rate when it reaches equilibrium again is lower than it was initially. So we removed CS2 concentration, a sharp drop in our forward reaction, i.e. favoring the reverse reaction, and therefore with the fewer particles that are left, considering we lowered the concentration of CS2, we now have a lower rate of equilibrium because there are fewer effective collisions. So that just earned us 1 mark over there. And then 6.4.2 over here says at 15 minutes, as we mentioned, another disturbance, the temperature was changed. Use Le Chatelier's principle to determine whether the temperature has increased or decreased. Explain the answer. So this is a 4-mark question, and it did have to do with what we were talking about up here for 6.3.3, this made up question, where we have increased heat in the system, where our heat is over here. So as we could see, there was a sharp drop previously for the 5-minute mark, which means we decreased the concentration of CS2. Over here, we had a sharp increase, okay, at 15, which means our temperature has increased. We increased the whole temperature, therefore affecting the rate of our reaction. If this dropped again, we would have decreased our temperature. So right now, for the first mark, we can just go ahead and write increased, because as we can see, the rate has increased very suddenly, meaning heat has been introduced into the system, which means if we have increased the heat in the system, just like we were talking about here, we are then favoring the reverse reaction, because the forward reaction is exothermic, which means the reverse reaction is endothermic, which just means we are favoring the reverse reaction. So we have written that it has increased because we're seeing this sharp spike in the rate, and an increase in temperature favors endothermic reaction. By that, once again, this is an exothermic reaction, but because heat is increased, it's favoring the reverse reaction because we added too much heat, which means it needs to go that way, which means if forward is exothermic, it means reverse is endothermic. And there was too much heat, which means some heat is going to end up moving on this side, which means our reverse reaction is favored, as we mentioned, seeing that our reverse reactions rate is above that of the forward reaction, and then they slow down to equilibrium. And then another mark for saying reverse reaction is endothermic. Another way on other memos in prelims and finals is just stating what type of reaction we have for the forward reaction so that we can then see how it opposes that. In this case, they didn't go for the forward reaction, they just stated that the reverse reaction is endothermic because that is the direction that it is moving in. Exothermic forward, endothermic reverse. And those 4 points increased. An increase in temperature favors endothermic reaction. Reverse reaction is favored. Reverse reaction is endothermic, earned us 4 marks. And then last question, 6.4.3, and it says, at what time does the system reach equilibrium after the temperature change? So when do these guys flatten off after this temperature change at the 15-minute mark? And as we can see here, it is at the 22-minute mark. Sometimes on the memo there will be leeway, but they have given us different increments, so we can see that they have then flattened off. The rate of the forward reaction equals the rate of the reverse reaction, and that is exactly what chemical equilibrium is, which means that they are now the same at the 22-minute mark. So we can just go ahead and write 22 minutes, and that'll be that. That'll earn us 1 mark over there. and 20 marks for this whole section. So if acids and bases is getting a bit confusing at the moment, we're about to break down question 7 here of the June 2025 chemistry paper. This is the last question in this whole paper. There isn't any galvanic or electrolytic cells in this paper, so we'll go through them in other papers. But for now, we're about to see what common questions come up in acids and bases, as well as some general tips to help us get a good overview to help orient ourselves in this section. So let's jump right in. So question 7 says, oxalic acid H2C2O4 is an organic diprotic acid commonly found in plants such as spinach. Okay. It is used in various industrial and laboratory applications, including cleaning, bleaching, and as a standard solution in acid-base titrations. So a little story here, not necessarily important besides the fact that we now know what we're looking at, the oxalic acid, and that it is diprotic. Other than that, it's just for interest's sake. So when oxalic acid ionizes in water, okay, so that's also good for us. They've given us the verb that acids do. In water, it follows the steps given below. So we have step 1, we have our oxalic acid and water. Our oxalic acid then gives away one of its H's to water. Okay, so that means water here is our base, our oxalic acid is our acid, as they've mentioned, which means HC2O4 is our conjugate base because it is now in the position where it is more likely to receive a proton, an H. Okay, then our H3O plus is our conjugate acid. It is more likely to donate an H, donate a proton. But then, as they mentioned, step 2, diprotic, is that we took our conjugate base, our HC2O4 with a -1, the conjugate base over here, we've taken it out of this beaker and we've put it in a new beaker with water again, where water is still relative to it, water is still the base, and this guy is our acid, which means once again, it gives away another H to water, forming our conjugate acid here, our H3O plus, and then we have our C2O4 2-, where we ended up losing 2 H's, and that's why we have a 2- here, because an H is a +1 on our periodic table because there's only one proton there. So whenever we're in acids and bases, we're just looking at the movement of H's, the donating of protons or the accepting of protons. And that means over here, this is our conjugate base, and this was the 2-step process, how oxalic acid ionizes in water because it is diprotic. So then from there, 7.1 says define a weak acid. Sometimes they start with Lowry-Bronsted, where we just talk about proton donors, proton acceptors. Other times they talk about the Arrhenius, which we'll break down further, just because that helps our application a lot more, where we have an acid ionizes in water to form a higher concentration of H3O plus ions, where we form our hydronium ions when we have an acid, or our hydroxide ions when we are working with a base and water. But in this case, we aren't looking at Lowry-Bronsted or Arrhenius, we're looking at a weak acid, which is more similar to Arrhenius. So a weak acid is something that ionizes partially. So the key word here is partially or incompletely, compared to a strong acid, which will ionize completely. So weak acids ionize partially in water, as we can see here, to form a low concentration of H3O plus hydronium ions. Okay, and this is a 2-mark question, 1 mark for here, and the other mark for here. And the reason ionizes partially, because it is a weak acid compared to a strong acid, which ionizes completely. And then a low concentration of H3O plus ions has to do with the fact that when we look at pH, we're looking at the concentration over here of our H3O plus ions, which means they aren't as strong on our pH scale. For example, we have scale of 1 to 14. Over here at 1, we have acids or very strong acids, and 14, we have bases or very strong basic solutions. Right here at 7 in the middle, that's our neutral, which means in terms of this definition, there's a low concentration of H3O plus ions, which means we're chilling somewhere around here. It's not neutral, but it is not a very strong acid all the way to the left. Okay, on our pH scale. We'll break down our pH scale in a later question as well. But right now, this is our definition for a weak acid, very similar to our Arrhenius definition, and that just earned us 2 marks over there. And then 7.2 over here says identify the acid-base conjugate pair in step 1. Sometimes they would say identify both conjugate acid-base pairs, but in this case, we just need to pick one. So we can either do this acid and this conjugate base, the H2C2O4 and the HC2O4 negative, the fact that that is the pair based on the fact that this A gave away one H to then become this, or we can look at our base, our H2O and our H3O plus. We can pick either one of those pairs and write them down and we can get our mark. Sometimes, once again, they just say write down both pairs and then we write down both. But in this case, we can just go ahead and write our oxalic acid, our H2C2O4, and we just put a little semicolon and we write HC2O4 minus. This is just the pair. We don't have to draw a line. This isn't about how the one becomes the other. We just want to see which one relates to which other one. And with that, this was step 1. If they said step 2, we would look at the second line over here. Otherwise, we just earned 2 marks over there. And then 7.3, also a very common question. These first 4 questions are just theory questions that are very common in just about every paper from June, prelim and final. And then we have our harder questions a bit later where we're doing titration and we have to look in different beakers, but we'll break those down. But then 7.3 here says give a reason why oxalic acid is referred to as a diprotic acid. So we have monoprotic, we have diprotic, and we have triprotic, etc. But we work with these 3 mainly, which means mono is something like HCl, for example. It only has one H to give away. In this case, di is like this H2C2O4 or an H2SO4, for example, where we have 2 H's to give away. And then this is rinse and repeat, where we have an H3PO4, where we have 3 H's to give away for a triprotic, which just means it can donate 2 H plus ions or ionizes to form 2 H plus ions. So this is 1 mark there, just mentioning that di has to do with 2. And it can donate 2 H plus ions, and these 2 H pluses are the 2 H's that it lost from here to here. They love that question, and then they also love 7.4, where 7.4 says the oxalate ion, this HC2O4, can act as an ampholyte. Give a reason for this statement. It is just saying give the definition for an ampholyte, which is when something can act as either an acid or a base. And that would earn us 1 mark over there, meaning that this guy over here can, in this scenario, give away another H where it is acting as an acid. But over here, if we were to reverse this arrow, right now this guy is a conjugate base, which means it has a negative, and if there was a stronger acid that it was in a beaker with, it would then receive from it and it would be the base. So it depends what we're reacting it with. If this guy is reacting with a strong acid like HCl, or in this case the H3O plus, we would then go back to our initial state over here, but it would act as a base. But in this scenario, relative to water, it is the acid giving away the H2 water. So it can act as either an acid or a base, and that just earned us 1 mark. And if ever they were to ask us to name the ampholyte in any solution, the most common go-to is water. H2O is the most common ampholyte that we have, and when there's a step 1 and a step 2, we usually have 2 options for our ampholyte, but if they were to ask us to name it, going for water is always our best bet. But here, they just wanted the definition. An ampholyte can act as either an acid or a base. And now we're getting to some sort of titration questions, especially this last question over here, a nice 10-mark question to finish off the paper. So then 7.5 over here, in a volumetric flask, 2.25 grams of oxalic acid is added to water to make up a standard solution to 250 centimeters cubed. So I just like to draw this section. It helps me visualize it a bit easier. So we have our oxalic acid, that is our H2C2O4. Just so we know which one we're working with. Okay, 2.25 grams, that is our mass over there, is added to water to make up a standard solution. The whole solution of H2CO4 and water together has a combined volume of 250 centimeters cubed. Great, so we have centimeters cubed, or we have 0.25 decimeters cubed in case we need the decimeters cubed for another calculation or a specific formula. Okay, so now we have all our information in a beaker and we have plotted it out so we can then visualize it based on whatever questions they ask. So then from there, 7.5.1 says calculate the concentration of the oxalic acid solution. Okay, so a 3-mark question over here. So we have our different formulas here for acids and bases. So we have this guy, we have that guy, we have this guy, and we have this guy. And if it is only 3 marks, it means we're usually using either this thing over here, C equals N over V, or C equals little m over capital M times V. And this guy is very common here for 3 marks, considering we have the mass, we have the volume. Great. We can always get the molar mass on the periodic table, and then we can go ahead and calculate the concentration. So this is just an isolation. We haven't mixed any acids and bases yet. We've just mixed the acid with the water to then make a standard solution. So that means we can go ahead and write C equals M over capital M times V. We want the concentration, which means we have the mass 2,25 over there. Okay, the molar mass for this guy, H, is 1 times 2. Then we have our C2, so plus C is 12 over here, and we multiply that by 2, and then we add oxygen is 16 over there, multiplied by 4, and that is just the molar mass portion. Then we have to multiply that by the volume, and this formula does require that we did the conversion to decimeters cubed. We cannot use centimeters cubed here. We can only use centimeters cubed in our titration formula because that has to do with ratios. So this has to do with ratios, which means we just have to put the 0,25 decimeters cubed at the bottom there as well. And then we can go ahead, we can plug this all in our calculator, and our answer is 0,1 mole dot dm to the -3, because the unit comes from the fact that we have our mole over our decimeters cubed in our initial formula. This is just the variation of this formula, combining this formula and this formula in one. We now have the concentration of the oxalic acid solution that has been mixed with water. Okay, so it's a little bit more diluted, like Oros and water, and that just earned us 3 marks over there. And then 7.5.2 over here says 25 centimeters cubed of the oxalic acid solution, okay, is titrated against sodium hydroxide. The average volume of NaOH required for neutralization is 28,60 centimeters cubed. So we have our H2C2O4. This is a follow-on question. So we had the concentration of this guy, and they only used this much volume of it. So they took a little bit of this guy out in some sort of beaker. Let's draw a different beaker over here. We have something like this. Cool flask, nice, which means we have the concentration of 0,1 mole dot dm to the -3, but they didn't just pour this whole amount into this other mixture. They just took a little bit, scooped it up, put it in here. We now have this much with a volume of 25 centimeters cubed, or we can convert that to decimeters cubed. So we have 25 centimeters cubed, or 0,025 decimeters cubed, and that's our volume. The visualization helps me, and very important to know what values we're working with in each beaker. But then, as they mentioned, the oxalic acid solution is titrated against sodium hydroxide. So sodium hydroxide here is from a different beaker. The average volume of NaOH required for neutralization is 28,60 centimeters cubed. So we have the volume of our NaOH over there, 28,60 centimeters cubed, or in decimeters cubed, it is 0,0286. And that is our decimeters cubed. And the fact that they titrated it means this is the point in time where they reach equilibrium. That is just the term. So right now, for a 4-mark question, a very nice formula to work with, especially considering they mentioned the words titration and neutralization, is this formula up here. Our Ca times Va over Cb times Vb equals Na over Nb. The one where we can do ratios, so we didn't necessarily have to convert our centimeters cubed to decimeters cubed, but either way is fine. So I'm going to go ahead and write that, and we can plug everything in so we can see how that works. So we have our concentration of our acid times the volume of that acid over the concentration of the base times the volume of that base equals the moles of the acid over the moles of the base. We don't always have to work with this formula, but it's quite nice because the moles in this case are just the numbers in front. We don't have to go ahead and calculate C equals N over V in this one flask to then get the moles, to then do a molar ratio, to then get the moles in the other guy, to then compare it. There's quite a few steps if we're working with this formula. So it's a lot easier and quicker provided we know how to work with this formula based on the fact that the moles are already in a ratio, and that's why we can use ratios quite nicely for this one, which means our acid is our H2C2O4. So the concentration of it was the 0,1 that we previously calculated in 7.5.1. So we have 0,1 over there. The volume, we can either take centimeters cubed or decimeters cubed, provided that if we take centimeters cubed here, we then have to take centimeters cubed over here, which means that our volume is 25 centimeters cubed for the top, so which just means we have to use the 28,60 for the volume of our NaOH, our base. And quick thing to keep in mind, if we are unsure about what our acid is, if they haven't told us explicitly or mentioned it in the name, we usually look for things with H's in front. Things with H's in front are usually our acids, and things with H's at the end or no H's in front are usually our bases. Besides water as the common pattern that usually follows the pattern for most of them. So just something to keep in mind where we're now working with the NaOH and not just water over there. But then our concentration of our base is what we want, because we do not have the concentration of the sodium hydroxide. So we can just call that X over there. And then our volume is 28,60 in centimeters cubed, because we used centimeters cubed over there. And then once again, our moles for our acid is just 1 over here, because we can just use the ratio of the numbers in front. And then our moles for our base, our NaOH, is 2 over there. So at this stage, 4 marks usually means this formula to work with. 3 marks means our original formulas from grade 11 as well. And then we can go ahead and just solve for X by moving some stuff. So we have 0,1 times by 25 multiplied by 2. So we move the 2 up there, and then our 1 can stay here, and we can move our X to the top over there. What we're doing is cross multiplying in one step, but if you prefer to move it line by line, that is also all good. Whatever makes it easier for us and helps us get an accurate and correct answer. So we move the X up top, and then what we're left with at the bottom is 28,60, because we moved the X and we don't have to move the 1 down. The 1 won't affect anything, which just means we can go ahead, plug this in our calculator, and our answer for X is 0,18. So it was 0,1745, which means they rounded up to 175, and then they rounded that up to 18. So decimal wise, it would have just been rounded to 17 if we went straight there, but they did double rounding in this case to get the answer on the memo of 0,18. And this is measured in mole.dm to the -3. And once again, we could just do centimeters cubed here and centimeters cubed here, or decimeters cubed and decimeters cubed. The ratios just divide each other, provided that we have the same units for both. And that's why we don't necessarily have to do the conversion to decimeters cubed in this calculation, which means we have our final answer over there for the concentration of the sodium hydroxide for 4 marks. And then 7.5.3, a theory question, says explain why phenolphthalein would be a suitable indicator for this reaction for 2 marks. So in grade 11, they would give us tables and they would tell us the amount of pH and everything. We could go ahead and calculate pH, but that's a lot of working for 2 marks with not very much information. Right now, we're about to break down a nice short way to remember which indicator is suitable for which type of reaction. So we have 3 different ones. We have our methyl orange, we have our bromothiamyl blue, and then we have our phenolphthalein. And we want to bring down our pH scale over here so we can then see what we're working with. So we're going from most acidic to pretty much neutral to basic. So that means for a methyl orange, we're at some range. Let's call it 1 to 3, for example. Bromothiamyl blue is chilling around 7. So anywhere from like 6 to 8. And phenolphthalein is from like 9 upwards. These are just rough estimates. These aren't important for what we're about to break down. But what is important when we're thinking about the pH scale is that it's kind of like midpoint. Is that if we have a very strong acid chilling over here and then a weak base that's reacting with it, we're going to end up with a midpoint of, not to scale, something over there, for example, which means we end up in the range where we are working with methyl orange. So methyl orange has to do with a strong acid and a weak base, because we're taking the midpoint of that strong acid and the weak base. And the way that I like to think about methyl orange is that orange is close to red, red will burn me, acids will burn me. These are just the links. These help some of my students. So that is what we're working with for methyl orange. Bromothiamyl blue is chilling in this middle range, which means we can either have a strong acid and a strong base, because then they are going to have a midpoint of somewhere in this range near neutral, or a weak acid and a weak base, because they are also going to have a midpoint at about 7. So we have a strong acid and a strong base, or a weak acid and a weak base. And that is just something to keep in mind there. There are a lot of dots going on here. And the way that I like to think about bromothiamyl blue is that your pool was green, okay, but then you had to add chlorine. Chlorine is some type of acid, and then once it neutralizes and your pool is blue, it is then good to swim, which means when the water is blue, it is good to swim, it is neutral, and you can swim without any hassles. So let me know if there are any other memory devices that you have in mind to know that bromothiamyl blue is neutral. I just like to think that if the water is blue, it is good to go and we can swim, and that is neutral, which then leads us to phenolphthalein, the last one, where we have a strong base and a weak acid, because if we have a weak acid over there and a very strong base over there. We have a midpoint over here, for example, and then we are chilling near 14, near our basic solution. And this is the explanation that they want. And the way that I remember phenolphthalein is that the most complicated word is the most basic. So it's kind of backwards in that it ends up being the most basic solution, but it is the least basic word. So most basic solution, least basic word. So that is just how I link that, which means we can then put these two words because they said phenolphthalein is the most suitable indicator, which means we're dealing with a weak acid, our H2C2O4, and we're dealing with a strong base. This is also just theory, something we have to know. So our strongest acids are our HCl, our H2SO4, and our HNO3. There are other strong acids, but these are the most common ones that we use in our syllabus, which means that any other acids that aren't these for the most part, and if they haven't pointed to the fact that it is a weak acid, are most likely weak acids. But then our strong bases are things ending in OH for the most part, and things in group 1. So we have an LiOH, an NaOH, and our KOH. Those are the most common ones. So we're looking in group 1 on our periodic table. We have NaOH, KOH, and LiOH. These are the common strong bases we work with, and then weak bases are basically anything else. So these are our strong bases, and then most of the other bases are usually weak then. And then something else to keep in mind for a weak acid, they kind of look like organic molecules, like acetic acid. Don't know it off the top of my head, but it's CH3CO something. And it looks like an organic molecule, and it is a weak acid. So what I've found is that these are just the most common ones they use for these strong acids and the strong bases, which means that if it isn't one of these guys for an acid, it is most likely weak. And if it isn't one of these guys for a base, then it is most likely weak. So then with that information, once again, they said explain why phenolphthalein would be a suitable indicator for this reaction. It has a strong base over here, this NaOH, and then it doesn't have one of these strong acids over there. Okay, it has this guy, kind of looks like an organic molecule, H2C2O4, and that is our weak acid, which means we can just go ahead and say that NaOH is a strong base and oxalic acid is a weak acid. And therefore, like we were talking about with the midpoint method that we were using, we have a strong base and a weak acid, which means our midpoint is somewhere above 7, which means our pH is greater than 7 because of the midpoint landing there based on how these two guys react. And there being more OHs left at the end than H3O pluses. Because what happens when these two guys combine with each other is that the H3O pluses, the little amount that it has for this weak acid, and the OH minuses, the large amount that the base has, combine together to break down to form water. But then at some stage, and we'll use an army analogy just now in the next question, is that these guys combine, form water, but then we eventually run out of H3O pluses because there's not enough H3O pluses because it is a weak acid, which means at the end, when we measure our pH, we're left with a lot more OHs, and that gives us a pH that is greater than 7 over here because we have no more H3O pluses, we only have OH minuses that have not been neutralized to form water again. So let me know if that makes sense in the comments below, but we will break that down in further questions and 7.6 when we look at one of these long questions, because this thinking helps us see what we're working with and why we have a more basic solution or acidic solution at the end. So with that, NaOH is a strong base, oxalic acid is a weak acid, and therefore the pH is greater than 7 over there. That just earned us 2 marks. And then 7.6 is the last question of this section and this whole paper for 10 marks. So let's get it. So the reaction between excess magnesium hydroxide MgOH2, I'll redraw this now as we've done in previous questions just to help see what we're working with, as well as draw the different beakers most likely. So we have the excess magnesium hydroxide MgOH2, a slightly soluble base. Okay, so they've told us it's a base, but it ends in OH, so that is helpful too. And nitric acid, which is an acid, a strong one, based on our previous discussion about indicators. Okay, occurs in an aqueous solution. Cool, so they've already been mixed with water, where it produces magnesium nitrate, a soluble salt and water. So there's like a salt precipitate chilling on top of this water thing according to the following balanced equation below. They've already balanced it. That's important for any molar ratios going forward. So I'm going to rewrite this for us so we can see what we're working with and attach the information for each. So we have it up here. I've left out the aqueous portions and the liquid portion, but that should be all right. We'll come back to it if need be. And now we can start to plot the information information they have for each. So they say 0.05 decimeters cubed of the MgOH solution. So we have our volume of 0.05 decimeters cubed, already in decimeters cubed, has a concentration, pretty good for us, cool, of 0.115 mol.dm to the -3. It's added to 0.02 decimeters cubed. So we're talking about our HNO3 solution over here. So we have 0.025 decimeters cubed over there, and it has a concentration of 0.095 moles, 0.095 moles.dm to the -3, HNO3 solution. So we're just for now working on this left side of our arrow over there in our reactants. And then it says calculate the pH of the final solution. So let's break this down part by part. So if we go ahead and we draw these two guys in separate beakers, before we combine them into one beaker, we will have something that looks like this. So we have our MgOH2 over there. We have our volume of 0.05 decimeters cubed over there. Our concentration of 0.115 mol.dm to the -3 over there. And then in a different beaker over here, which is our HNO3 over there, HNO3 over there, we have a volume of 0.025 and a concentration of 0.095 mol.dm to the -3. So right now these guys have different concentrations, different amount of OROS in water for that analogy, and different amount of volumes. So they're different sized beakers. This guy's a little bit smaller than this guy. But then what is happening? They say they're combining them into one beaker. They're mixing each other, and the reaction between excess magnesium hydroxide, which means there's more of our base at the end, which means we have a more basic solution. Okay, so we've combined them. Usually the volumes are additive. We'll see if that is something that they're mentioning here, but we're adding them and they're reacting. The OHs from this guy are reacting with the H3O pluses from our very strong acid, but in this case, there's just not enough volume of it to neutralize this base, which means OH minus, H3O plus. In this case, let's say we have an army of 4 people, for example. And on this side, we have an army of 2 people. These are our H3O pluses from our acid. These are our OH minuses from our base. The fact that it has excess magnesium hydroxide at the end of it means that in this war, one of these guys will take out one of these guys and give away an H and form water on both sides. Okay, so that becomes water when H3O plus gives an H back to OH, because then this becomes H2O and that becomes H2O and we have water, which means we continue with this analogy. Another guy takes out another guy in this war, and we're left with our excess magnesium hydroxide. We're left with an OH, meaning that on our scale over here, we had 1, we had 14, we have 7 over there. We're ending up being basic. So when we plug something into our pH equation, we might have to get our OH first because we end up with a pH that will be pretty high. So this is also something to keep in mind to help see that our answer is in fact high. If it is low or neutral, we have done something incorrectly because they said there's excess magnesium hydroxide. And if we know that this guy is in excess over here with OH minuses at the end, the way that we're going to get there to get our moles for our excess is to take the moles of the initial minus the moles of the reacted, because we want to know how much is left. This will tell us the pH of the final solution. So this is the setup. The excess is how much is left, which means we have to take how much we initially had from our MgOH, okay, which means we can calculate that in this beaker and subtract it from the amount that reacted. But we don't know how much reacted from this beaker, but we do from this beaker, because this was our limiting reagent, which means all of this ran out, okay? Which means to calculate the initial moles for this guy, we can then do our C equals N over V for this over here, this MgOH2. And we want the moles, which means we have the concentration in this beaker in isolation, which is 0.115 over there. The moles is what we want, and we have the volume in decimeters cubed already, so that is 0.05 over there, which means we can just go ahead and figure out the initial mole amount in this separate beaker for MgOH2, the initial amount in terms of moles. So if we times our 0.05 up over there, 0.00575 moles. And this is the amount of moles that we had in our beaker initially. And then at this stage, we need to see how much actually reacted of this. So that means we're working on this side where we have to work with our HNO3. we're going to treat it exactly the same as we did the previous one in isolation. We're then going to do a molar ratio from HNO3 to MgOH because they have a different amount of moles that ended up reacting. Because we're just looking in isolation, or we're trying to, at the MgOH2, the base that is in excess, because the excess, the leftover, is what will tell us our pH, which means over here we can then do the same calculation with different values for our C equals N over V for our HNO3. Okay, so our N is what we want, our C was given to us as 0,095, and our volume was given to us as 0,025. And then once again we can multiply the 0,025 up to the 0,095, and our answer for our moles is 0,002375. A reminder that this guy has to do with our HNO3, and in this formula here we're looking at our MgOH2, which means we have the initial, we calculated that previously in this first beaker, so we have 0,00575, and then we need to see how much of it reacted completely with the thing that ran out first, our HNO3. By that we have the amount of HNO3 in terms of moles, but we just have to do the molar ratio from our HNO3 to our MgOH2, which is a 2:1, which means HNO3 over here to our MgOH2 over there. HNO3 had a 2 over here on our initial equation, and MgOH2 had a 1 over there. So that is their molar ratio, so we can then get the amount of moles of the MgOH2 that did react, which means we calculated in isolation the amount of moles of HNO3, which was 0,002375, and then if we divide this by 2, we have 0,0011875. And now we have the amount MgOH that did react in this beaker, because this was the total amount of HNO3 that did run out, the limiting reagent, and then we did a molar ratio to get the amount of moles of the MgOH that did react. So the initial minus the reacted, which is that answer 0,0011875, the initial minus how much did react will give us how much is left over, because if all of it reacted, we'd go this whole answer minus that whole answer and we'd have nothing left. But they told us that it is an excess, and excess means we're left with OH minuses at the end. We're left with our MgOH2 in this beaker, which means we can just go ahead and subtract these two answers, 0,004565, and this is in mole. And then at this stage we have the amount of moles in excess of our MgOH2, so it is the whole MgOH2. But then in order for pH, we need to calculate the amount of OH minuses that are left in this beaker, which means at this stage we have to do a molar ratio inside of this compound, where we have the amount of moles for the whole thing, and then we have to compare it to the molar ratio of the amount of hydroxides that can break off for this base. So we keep zooming in, we keep moving from beaker and beaker, and what makes this section trickier is that we're changing the context by which we're measuring things, which means that if we have our MgOH2, this is the amount of moles that is left in the beaker in excess, and then we're comparing it to our OH minus, the amount of hydroxides that can break off, and there's a 2 over here, which means we're going to multiply this by 2, because there's one whole MgOH2 over there, and then there will be 2 OH minuses that can break off inside of this compound, which means we have to do a molar ratio of 1 to 2, multiplying this answer by 2, which means we have 0,009125 for the amount of moles of OH minus ions inside this beaker. And now that we have the moles of the OH minuses that are left in excess, we can then go ahead and get the concentration of that, because then from there we've done a whole lot of stuff with moles that we can then try and get a square bracket over here having to do with concentration. So if we are working with C equals N over V, this is all for our OH minus ion, we have this answer for our moles, so we have 0,009125 over there, and then volume at this stage we have to see we're in this big beaker over here, which means we are not the 0,05 over there or the 0,025 over there. They haven't mentioned it here, but they usually do in papers say that the volumes are additive when we add them into a new beaker, which means that the 0,05 plus 0,025 gives us a total volume of 0,075 dm3. We're just adding the amount of volumes. If you were to pour Pharos in one and Sprite in another, this would be the collective volume. They would add up directly. And that is how we treat these questions when they are added to the same beaker, which means that this will be our volume plugged into this formula because they are now in one bigger beaker with a new combined amount of solution, which means we can write 0,075 over there and then plug this answer in our calculator. And for our concentration of our hydroxide ions left over, we have 0,12166 mol.dm to the -3. And at this stage, we have earned 6 marks. We are 4 marks away from our answer, but now we actually have the amount of concentration of our OH- ions specifically in this beaker at the end, because this excess magnesium hydroxide is what is remaining. We've run out of our HNO3 and we only have our MgOH2 in there that is broken off, and we have our OH- ions that could not be neutralized because there were not other H3O pluses to neutralize them. So that means we're just working in pH land, and now we can go ahead and write down these two formulas. We haven't started in H3O plus, and in order to get pH we need the H3O plus, which means we need both of these formulas. So we're going to start in this formula over here, and we can rewrite this portion over there. So I'm going to go ahead and do that. Okay, so we have our Kw, which isn't as important, but it is there, which is the concentration, square brackets, of our H3O pluses multiplied by the concentration, square brackets, of our OH- ions equals, the value is what is important for this equation, 1 times 10 to the -14. It says at a certain temperature, 298 Kelvin, but they didn't specify temperature. But if ever we have OH- ions, we have to work with this formula, whether they speak about the specific temperature or not, unless they specify another temperature and another value amount for this, which just means we can go ahead and write 1 times 10 to the -14 equals 1 times 10 to the -14. So then, ignoring that portion of it, because that is just the symbol we're looking for, we have the concentration of our OH- ions, which is over here. So we have 0,12166 over there, and we want the concentration of our H3O plus ions, so we can plug it into our pH, and this just remains on the right side over there. So now we're just treating it like a normal sum, imagining that this whole thing is X. So we can go ahead and divide our 0,12166 on both sides, and our answer there for our concentration for H3O plus ions is 8,219 times by 10 to the -14. That is a multiply over there, and that is a -14. And now we have the H3O plus. The reason we need our H3O plus is because that is the H in pH. Okay, we aren't getting the POH over there. We don't want this guy. This is a different method of doing it. We don't want the hydroxides. We want the H from our hydroniums. And now we have that, which means we have it in terms of this last equation. So we can just go ahead and write this down and solve for our pH, which means pH equals negative log of the concentration of H3O plus ions, which means we just need the pH. We aren't unwrapping logs in this scenario. We can just plug our values in and solve for it in our calculator, because H3O plus, the concentration of it is this whole value over here, which means we have 8,219 multiplied by 10 to the -14. And that means our final answer is 13,085. And based on our initial statement, we knew that there'd be more hydroxides left, and therefore we would have a more basic solution. And in this case, it is very basic, chilling almost all the way at the top of our pH scale, with acidic being here, neutral being there, and basic being here, meaning that that was the final answer for the pH of the final solution. That earned us 10 marks over there and 25 marks over there for the last question and last section of this paper. And to reiterate, we got the moles of the initial. So we had our MgOH2 over here in one beaker, which is our base that was in excess, the HNO3, our acid that was over here in another beaker, and that was what ran out first. We poured them into one beaker and they reacted, and then we were left with an excess magnesium hydroxide solution, meaning that our solution ended up being more basic, which means we were looking at moles first, and in order to get how much was in excess of our MgOH2, we then had our initial from the first beaker, plugged that in, minus the amount that reacted completely, because the HNO3 reacted completely, but then we had to do a molar ratio to get it in terms of MgOH2. So we had how much was here minus how much reacted, and then we had how much was left over. From there, we then did a molar ratio inside our compound, inside our MgOH2, comparing our MgOH2 to our hydroxide ions that actually remained there, because we need our hydroxide or our H3O pluses in order to calculate pH. And in this case, it is more basic, so there's more hydroxide ions. Based on our analogy, there not being enough H3O plus ions to neutralize the OH minus ions with this army that we had going on. Okay, so we then did a molar ratio inside our compound, comparing the amount of moles that we had in excess for the whole compound compared to the amount of OH minus ions that would break off. Once we were there, we then calculated the concentration of that amount of moles of the OH minus ions over here inside the additive volume of this whole beaker, because the volume of these two guys added up, and that is what we were dealing with here to then get the concentration, these square brackets for just our OH minus ions, which means we're now in pH land, where we could then go ahead and plug into this first equation where we have a placeholder for the concentration of the OH minus ions, and then can calculate the H3O plus ions, because that is what we need based off of this constant in order to plug into our actual pH calculation. Based on the method that we were using, there is another POH method, but we didn't use that method. We might see that in other later videos, but it helps to find one method that works and stick with that, because then here we had our H3O plus ions, the concentration of it, and we could then plug it in to our final equation to get the actual pH of this final solution, which is very basic based on the fact that we had more OH minus ions left at the end. Great job, guys. Let me know if there are any questions in the comments below and I will get to them, and otherwise I will see you in the next video.